things. I finished my PhD in South Korea with optimization as a background. So I'm from power system background before. So I chose this topic to work on multi-agents for active building. And parallelly, we are planning to work on multi-agent systems for multi-energy systems. So because heating and hydrogen and electricity when the integrated problem. So we would like to work on that.
Got it. Got it. Okay. Thank you. Thank you, Srinath.
Thank you.
Nayan Manna.
Hello, sir. Good evening.
Good evening. Good morning. Yeah. Man.
Yes, sir. Sir, I am actually doing my research in Jadavpur University. So my topic of interest is analysis and design of AI-based grid management system for distribution network using distributed generation. Specifically, I am working on wind and solar.
Okay. Very good. I think that's a very good topic. Application of
Yes.
AI. Yeah.
Yes,
The
sir.
only problem, the AI, if I have to say one line for AI. So AI is a very good search engine. Okay.
Yes, sir.
That's if one line describe AI, is very good search engine as of today. Okay. I
Yes,
don't know
sir.
whether it change or not, but okay.
Yeah.
Thank you.
Yes. Sir.
Dipayan.
Okay, sir. Thank you, sir.
Hello, sir. Good evening.
Hi, Dipayan.
Good evening and good morning to you, sir.
Good evening. Good morning. Yeah.
Sir, actually, I'm currently working in the control systems domain. Uh, Parametric estimations, signal systems estimates, adaptive controller designs, cyber physicals analysis. So all these things that we are planning to apply to a nonlinear dynamical system so as to control their performances. So currently we have submitted 2, 3 project to Government of India related to that cybersecurity coordinated controls. So currently we are working in that area.
Very good. Very good. Okay. Very good. But Dipayan, you said several areas, right? Adaptive. You can't do everything, Dipayan. So you have to narrow down what really you are enjoying.
Actually, sir, all the things are coded somewhere. Yes, sir. Yes.
Okay.
To
Okay.
understand these topics are correlated because only have a plant, we cannot go for the design of a controller. So that's why we are going for the estimations of signals and systems. And then we have to develop the control systems for ensuring the desired performance. So we are
Got it.
working in that area to develop adaptive control framework.
Got it. We just recently published one paper on unknown input observer applied to microgrid. So you should just look at it. It's a IEEE transaction paper. Okay, I think looks like I
Sure.
really love to hear from you and share everybody's research here. We are running out of time, maybe 5 more minutes. Okay, so quickly, just tell your name, institution, and 1 or 2 line description of your research. Okay, so Sovik Mondal, if I don't know whether you have done it or not. Sovik Mondal. Okay. Panduranga Vittal.
So Namaste, Professor.
Okay.
I am from NIT Surathkal.
Okay.
I work in the domain of digital protection of
Okay.
power system and distribution systems.
Very good. Very good. I think protection is in very much demand with renewables. Okay. A lot of problems are there.
Yes.
And I heard that adaptive is also not working.
Yes.
So it's really challenging, challenging, system specific, lot of work for the protection researchers.
Really true.
Thank you very much.
We are
Thank
at challenge.
Yeah, I lost you. Okay. Sadasiva Behera.
Good morning, sir.
Good morning.
I am Sarasip Behra from NIT Silchar. Currently, I am doing on energy management study in microgrid systems.
Energy management. Okay, very good. Thank you, Sadasiv.
Thank you, sir.
Nayan Manna.
Yes. Hello, sir.
Hi, Nayan.
Yes, sir. I have already talked to you.
Okay, you already, because my screen is like changing.
Yeah.
Okay.
Yes, sir. No. Sir.
Vaibhav Vaishnav.
Good morning, sir.
Good
I'm
morning.
audible?
Good evening. Yeah.
Good morning, sir. And sir, I'm a PhD scholar from IIT Jodhpur. And presently, sir, I'm working on distributed secondary voltage and frequency control of microgrids using the multi-agent consensus protocols.
Okay,
So, yes.
very relevant. Very relevant. You got a lot of information. So I think definitely you saved 2 months of time for sure, right, Vaibhav?
Sir, maybe I can't say right.
Maybe, okay. Yuvraj, thank you, Vaibhav. Yuvraj.
Thank you, sir.
Good afternoon, sir. Sir, this is Yuvraj from Sony. I am pursuing my PhD in IIT Roorkee, and my topic is performance studies in rural microgrid. So basically, I am trying to implement some artificial intelligence technique into some voltage improvement performance and so for some performance analysis.
Got it. Thank you, Yuvraj.
Thank you,
Monica.
sir.
Good evening, sir. I'm Monica Mishra. I'm a research scholar at IIT BHU, and currently I'm working on decentralized peer-to-peer energy sharing.
Okay. Thank you, Monica. Jyotsna Singh. Okay. Santanu Srivastava.
Good afternoon, sir. I'm a research scholar from MNNIT Allahabad, and my research area is energy management of microgrid.
Okay, energy management. So someone else also said energy management of microgrids. I think you should collaborate with that student or faculty here. At least exchange your ideas after this tutorial ends. Okay. Remember, today is the last day, and we have to talk a lot about it. Okay. So, and maybe 2 more minutes. Okay. And then probably in the break, we can do that. Okay. So, thank you, Santanu. Ravi, Rakesh Kumar, Trivedi. Okay.
Yes. Good morning, sir. Sir, I am from MNIT Jaipur, and my research topic is peer-to-peer energy trading using game theory models.
Game theory model. Okay. Very good. I know one guy, Gopal Gajjar. He has done some good work in game theory, but that was very long back. Okay. He's from IIT Bombay. And many times he writes in Power Glove. So I think you can reach out to him if you have some questions. Gopal Gajjar. Okay, his name is. Sunita. Thank you, Ravi. Yeah.
Yes.
सुनीता जी आपका आवाज नहीं आ रहा है, so maybe we'll come back to you. Yeah, thank you very much. Okay, I think it's 7:50 here. One more last. Okay, Ashish Prajesh. Ashish, are you there?
Yes, sir.
Okay.
Good afternoon, sir.
Good
My name is
afternoon.
Ashish. I'm from MNIT Jaipur. I'm PhD scholar over here, and under the supervision of Dr. Prerna Jain. And my topic is electricity price forecasting.
Okay, price forecasting. Very good. Mohammad Saidepur, you have heard about this professor? Mohammad Saidepur is from IIT Chicago. He has a lot of books, lot of papers, and he has devoted his life on optimization of unit commitment, price-based forecasting. So you can see his papers, okay, for your research, Ashish. Okay, then thank you very much. And sorry, I could not reach to everyone. Okay, I really wanted to hear from everyone, but I think looks like everyone are doing good research. Means, okay. Okay, so give me 1 minute, and I will pull up my presentation. Okay. And Okay, and a quiz is there for sure, but I try to be short this time, okay? Because we want to cover other aspects of this one as well, okay? Okay then. Remember, this is the game pin. You need to go to kahoot.it. Okay, very good. Okay, very good. Okay, I know this may be tough one, okay, but if you got it, that means you are reading, you are doing your job basically as a student. All of them. That's very good, very good. Okay, 15 students, huh? Okay, this was tough one, okay, but if you have gone through it, I think that's credible, means that's credible. Those are devoted students, I would say. Okay. Not bad. 9 out of 12. Okay. 9 out of 12. 10 out of 12. Okay. That's impressive. Subal, congratulations, Madhu and Somal, Swati and Nitesh, and everyone who participated, everyone who has read the presentation, I think. So that's good. Okay, 63%. So every day our score was increasing. So I think this is amazing. Okay, I think you guys are doing very good. Okay, so I think let's start talking about today's lecture. Okay, but before I start, because I heard a lot of students about research, exciting research. Research will not produce fruit. Research will not produce fruit if research is your secondary task. Okay, so any of you, this is over the years I learned, okay, research will produce fruit only if you are devoted to research. If you are thinking day and night, what is next, okay, how I can figure that out, okay, coming up with the right questions, okay, and then you can find the solution. So please make sure that you understand the fact here. Result, algorithms, writing papers will not come just at your door. I am available, just take it. Nope. You have to work hard. You have to make, this is your golden chance to go from wherever you are to the next level. Okay. And if you don't take this chance, you lost the opportunity basically. Okay. So, and I say that it's not easy. Okay. And not for everyone. Okay. But if you are persistent, if you are doing it, you can do it. Yeah. Okay. So good morning and good evening. Okay, so today a lot to talk about. Okay, let's say start with here, right? We now probably already we talked about control center. Okay, many here. This one is PJM, Pennsylvania. This one is like 7 or 8 states. This PJM monitoring. Okay, the market and all generation, transmission, interstates are monitoring here. Okay. And I have heard a lot of microgrids. Okay, microgrid cannot be possible without communications infrastructure. Okay, so if you don't have good communication infrastructure in your power grid, microgrid cannot be possible. For microgrid, you need good data, good quality data to make the microgrid work. Okay. Initially, like 10 years back, the challenge for the microgrid was to disconnect and reconnect to the grid. Okay, just disconnect. That was the biggest challenge. Okay, without turning off. Means you can definitely turn off all your microgrid and disconnect it, and then, but without turning off, how you can disconnect and reconnect. Okay, that was the biggest challenge. Okay, 10 years back. Now I think the biggest challenge is making so many renewables work together. Okay, I would say. So communication is very important for the microgrid. Okay. What is smart grid, right? Means most of you probably know what is smart grid. Okay, so what makes the smart grid? Okay, so we have automated meter reading infrastructure, PMUs, phasor measurement units, energy management system, the distribution management system. Once you have this one, okay, and you are utilizing this one to do some kind of a control, some kind of management, okay, then we can call it probably a smart grid. Based on electricity prices and weather forecast, okay, all home appliance schedule their consumptions. Okay, so can we do that? If we can do that, then probably we can say that this is a smart grid. Okay, predict cyber attacks and mitigate them without human interfere. Okay, if we can do that, I know that so many of you are working on it, right? And remember, you cannot solve multiple problems. You have to find out one problem, and just solve that problem. You cannot work on multiple problems. Then you won't you will just get the gist out of it. You won't be the expert. But if you solve one problem, then probably you will be the expert on that one. Zero outage in electric grid. Okay, if we have that one, probably we can call it a smart grid. Okay, energy bill reduced to half. That is the demand for everyone, right? Everyone. This one. In US, Department of Energy says that smart grid generally refers to a class of technology people are using to bring utility electricity delivery system into the 21st century using computer-based remote control and automation. Okay, but for a researcher, these are the questions. What are the drivers, right? Why is important, right? Of course, in US, workforce aging, new energy market, separation of generation. We talked about vertical integration, horizontal means, right? So energy market restructure, because now many of the states are restructured here. So we can do like a competition, right? Kind of thing. New technologies bringing in, coming in, like PMU we talked about, right? Growth in energy consumption, that is one important driver. We saw that tremendous energy consumption, okay? Energy independence, okay? To make us energy independent, okay? Using these new renewable sources, okay? And this is just kind of a cartoon, but that's okay. Okay. So what are the new technologies? Pressure measurement units, wind and solar, most of you are working, power electronics inverters, right? AMI, battery storage, different kinds of battery storage, okay? But for us, power engineer is just utilization, dumping, right time, taking out, right time, how fast we can get it. That is again a very challenging issue from the manufacturing side, the material that is used in the battery storage. Okay, plug-in hybrid vehicle. Okay, right now I think there is no challenge, but when it will in next couple of years, the consumption market will have a good amount of share from plug-in hybrid vehicles. Okay, so then charging infrastructure gonna be big challenge. Okay, big challenge, and charging fast. Even still, here we have a lot of cars. They have these cars are plug-in hybrid vehicle. Only complaint we have to spend a lot of time in charging. Okay, if we are traveling, we are spending a lot of time in charging. Okay, so charging is a big concern. Okay, charging is big concern here. High performance computing, communications, right? Technologies. This one. So how will be the next generation grid, right? We talked about, but definitely digital, right? When we talk about smart grid, that is 10, 15 years now, a $10 billion investment. So 10 billion is like bucket in a, we need bucket of water, and this is a drop, okay, $10 billion. So we need a lot of research, a lot of capital, and multiple party, okay, not just electric utility, policymakers, everything together, that really we want to do it. Then only it will be possible. Okay, two-way communications, monitors and sensors everywhere now. Because of this investment, a lot of new sensors are coming that you can even install that in distribution side and get the synchronized measurements. Self-monitoring, self-healing, self-optimizing, right? That is what we want from the grid. We don't want, there is no way, right? It means this is working 24/7. So if some important, urgent, transient issue we want to resolve, we want that grid should be able to resolve it. Okay. Customer choices. Customers should have a lot of choices. We'll talk about it definitely in the demand response, that okay, what it means. Adaptive protection, we talked about, at least very important. Okay, accommodate generations through all sources, right? Not just wind, solar, biomass, everywhere. Means all generation that you can generate you should be able to accommodate into your grid, and you should be able to use all available measurements. Okay, SCADA 2-3 minutes, even AMIs maybe 10-15 minutes or hourly, however it is configured. Okay, PMUs second, millisecond. So everything put together on you can leverage it, okay, for making your grid smarter. We want to make our grid more efficient, okay, and then definitely more efficient transmission of electricity, and efficient in general everywhere, right? We want to reduce the losses wherever possible, right? Quicker restoration, we already saw a couple of examples that it is possible, right? After power disturbance, and quicker restoration, and the impacted area, I mean fault wherever there is an impact, we should minimize that area, outage area. Okay, so that is a need of the research on that one. Yeah, coming up with one. It is possible. It is definitely possible, but you need infrastructure for sure. Reduced operations and management costs for utilities, and ultimately lower power costs for consumers, right? Reduce peak demand, which will also have lower electricity. We'll talk about again how we can do that, reduce peak demand, right? And every extreme cold, extreme heat, sustainability of grid without even breaking it, that is a big things for the operator, power operator. Okay? So increase integration of large scale renewables. Okay? Definitely rooftop, residential, but large scale renewables. I think I was visiting in Germany 2015, and I don't know from where I was traveling, but I was traveling to Germany by car from probably west to Germany. So I was coming from the west, probably Hungary or I don't remember, Austria or somewhere. I don't remember the place, but I was traveling to Germany, and at that time, for at least 20 minutes on my travel, that was 180 kilometers per hour speed on Germany highway, and 20 minutes both side. Wherever I can, means how much ever far I can see both side, I saw solar farms installed. Okay, in that highway, both side, how far I can see it, that far solar farm installed. 20 minutes. Okay, so that's many countries are. I mean, by now it might have grown a lot, but of many countries, our India is doing a lot on, I think 350 gigawatt in somewhere in Rajasthan, if I'm right. There is a plan from Prime Minister Modi. So those are good things. Okay. Better integration of customer owner power generation systems, right? Including renewable, and improved security. That is also important, right? Security. Some of the technical challenges from the utility side. Okay, so these are like immediate challenges, I would say. Okay, immediate challenges, not research challenge, but immediate challenges from the infrastructure side on this one. Okay, cyber secure communication. Okay, SCADA system and field devices, whichever is sending the message, sending the data to the control center. AMI and in-home devices, that is communicating with the grid, right? Or utility. So that is definitely a challenge. So that someone should not hack into it, right? And modify that. Because AMI, someone can definitely steal it and do research on it, how we can modify, right? And large scale cyber attack can be done, I think. Communication bandwidth and availability, right? That is the biggest challenge in rural areas with long circuits, even in United States. Okay, densely populated area is also communication bandwidth is challenging, right? Because we have a lot of people, so we need this one, communication bandwidth. Dynamic voltage control, industrial customer with sensitive loads, right? Frequency regulating with battery charging, right? So those are dynamic voltage support, technical. These are immediate, I would say. Okay, immediate challenges, moment. Harmonics, harmonic level, someone was asking, right? Harmonic level is real, right? Because whenever you have inverter switching, you will have harmonics. What are effects of high level of harmonic? Not my area, but I have not heard much about it. Means there may be some papers out there, but I have not heard much about it. I mean, that's a good topic if there are not paper out there, not a lot of paper out there, not in-depth study what is happening with harmonics, with renewables in the grid. Okay. Forecast master's level project. This one definitely master level. Every day 10-12 hours of work can be possible. Forecast of future harmonic levels with additional inverter type loads, right? How do we reduce harmonic levels? Okay, it's very well laid out techniques out there for reducing the harmonics, but now that those techniques are kind of more like centralized, right? This is everywhere now. We have rooftop solar, okay, and if these solars are dumping power onto electric grid, that means they are also injecting harmonics, okay. So distributed control, and you need some kind of control, right? So that you can reduce the harmonics. Again, I think it's challenging problem. Okay, it's challenging problem. Unless somehow we make a controller with renewable that will take care of itself, then I think probably solvable. Okay, this one. Okay. Okay, so these are research needs. Okay, some are immediate, some are futuristic. And I think most of you are working on it. Okay, so that's a good thing. Demand response, at least definitely a lot of things have happened for last several years in United States for demand response, and there are success stories out there. So that's a good thing for demand response. Distributed energy resources integration, we already mentioned that we have about 13% overall in US. Right? Those are, I think, a good number, okay, but not the number as power system engineers want to see, and not the number that can help a climate crisis that going on in the world, right? A wide area situational awareness, that is a lot of things is happening in United States because we have infrastructure now. We have thousands of PMUs in transmission system. We are still not in distribution system for wide area situational awareness. So current research is going on in distribution, but the infrastructure is not there. Okay, but we definitely have infrastructure for transmission system. We can get data real time, synchronized data for, I think, almost all transmission grid. Okay, so a lot of applications. In RTDS, I think is a good tool for doing some kind of hardware in the loop simulation or power hardware in the loop simulation for wide area situational awareness with some kind of AI. I think that would be good moment, means momentary, good moment of the right moment for doing AI, for applying AI for situational awareness. Okay. Battery storage, electromobility, right? Means electric car charging, discharging. So electric car now can be used as a generator, right? Can be used as a load and is not fixed at a location. So wherever the user is going and wherever there is a charging, user is going to charge. So the mobility comes in. So now your load is mobile, right? Or your generation is mobile. So it's a lot of research going on, has been done, but it's not completed. There are still challenges out there. Okay. So if you have, I have not heard anyone is doing electromobility from any, maybe some other students that I have not talked about it, but that is a good thing. But you need a transportation expertise, okay? Because you need kind of finding out pattern, right? Means finding out, so you need to link with your, in reality, you need to see where people are going to work, what are their timings, what is the infrastructure, a lot of things, right? You have to figure out to see the impact of this mobility on the grid. Okay. Cybersecurity, biggest problem, okay, and unsolved problem as of yet. Okay, restoration is also unsolved problem. Data networking, AI, lot of buzz in AI. like I said, AI in one line is right now the capability that we have for AI is very good search engine. So if you AI in your model, if AI has seen something, it will find something when you ask it. If you AI has not seen, then it won't be able to find it. Okay, at this stage in time, maybe 10 years from now, we don't know. Okay. Advanced sensing, intelligent controls, distributed computing, automations. Okay, those are the research needs. Okay, intelligent controls. Okay, a lot of you are working on microgrid. This is intelligent control is very well applicable to microgrid. Okay, distributed computing. Distributed computing probably is good in transmission system. Okay. Okay, so that's the smart grid. Little bit about demand response. Okay, so what is demand response? Okay, so demand response is not demand curtailment. Okay, so if you are curtailing, means you are or shutting down something, then it's not a demand response. So our PGM says, what is a demand response? Demand response is a consumer's ability to reduce electricity consumption at their location when wholesale prices are high or the reliability of the grid is threatened. Okay, so with respect to prices, they are saying, okay, prices or reliability is threatened. Means that if you don't do demand response, probably your grid will shut down. Means you will have blackout or some serious things will happen. Okay. So it's either due to high demand, high temperature, low temperature, or some extreme weather conditions, right? Common example is already implemented in the United States that we can control thermostat. Okay, thermostat. Utility can control the thermostat. Okay, utility can change the brightness of the bulbs inside your house. Okay, through some kind of price signals, okay, or directly control it. Okay, so one example in Washington DC area, I forgot the utility name. I'm not remembering the name, but they created kind of bilateral contract between utility and consumers. So consumer get maybe $25-50 credit every month from the utility, and in return, user will allow utility to modify the temperature by 5 degrees. Okay, so whatever you have set it up, 5 degrees, it can change the temperature. Utility can change, and there may be a time also, maybe 30 minutes, and couple of maybe 4 or 5 times in that particular season, summer season or winter season. Okay, so those are implemented and it's working in the United States, thermostat control. So utility can send the signal to the thermostat, change the temperature, but then user come back, you can say, I'm not feeling comfortable, you can go and change it, right? But now I think they are implementing that if user come back and changes, means come back and change the temperature, then they will penalize, because user created a contract with the utility to receive some credit, $25, $50 credit. Okay, so a lot has been done in demand response. Okay, this is one aspect of it. There are other aspects from the utility. This is from changing the some kind of devices in the house, consumer houses, right? Utility, two possibility for doing. One is for economic operation, you do demand response, and one is for the emergency. Either emergency for weather dependent, in the emergency because we don't have enough generation, so whatever is the case, anytime it's going to shut down your, whenever you have a chance of a blackout, okay, or chance of a lower voltages, right? Lower changing of the frequency. Definitely, whenever we talk about frequency, that means there is a demand and generation imbalance. So, and definitely some economic aspects as well. Okay. Demand response is changing the load shape based on price signal. Okay. it is a key to mitigate market power. Okay, so what was happening in the United States is that now we created all the market, right? So generation, transmission, distribution, and now whenever we have a peak demand, either in extreme cold or extreme heat, okay, this generator company, because their job is to maximize the profit, right? And in California, sometimes cost of this electricity goes up to $1,000 per megawatt hour. Anyone remember what was the cost of megawatt hour that we discussed in day one? About $80. Okay, and in India we have about $40, $38. Okay, so prices, and this is real. Okay, so $1,000 per megawatt hour in peak. And for Texas, I have read some news that during Texas blackout, if you have not heard it, very big deal for the United States. And I have seen the reports that users whose lights were on during that time, they received like $9,000 electricity bill. Some received $3,000 electricity bill for that cycle. Okay, because the prices was so high, and that prices they have to pay to that because it's a contract, right? And then if you are consuming, you have to pay, and at the end, consumer has to pay that. Okay, but I think the policymaker came in and did something, but I am not aware of it. Okay, but I think there was a talk, because no one can pay $9,000, right? So market power. So those kind of things we can mitigate. So with demand response, but again, certain limitations. With demand response, objective is not to shut down the load, right? Demand response objective is either you can shift the load, or you can somehow manage to lower the consumption of that load, right? So if there is some kind of peak is happening, maybe a 30-minute, or we know that 30 minutes we don't have enough power, right? So that 30-minute duration, can we tap into these millions of customers, right? They have signed the contract with us, and everyone is going to change their consumption, means then probably we are going to achieve that kind of demand response. And if I read report correctly from the FERC, they are mentioning they got about 13 gigawatt of demand response in 2018 and 2019. 13 gigawatt of demand response, that is on the paper. Okay, on the paper. So probably more than that, but 13 gigawatt they can do it. Okay, so that is for definitely helping the grid. Okay, and definitely helping consumer, because now you have a power to mitigate the market. Okay, whatever market has the power, generation company has power, right? Because they know that not enough generation, less increase the price, demand and consumption. Key to restore high priority loads, right? It's help us restore high priority loads. Key to manage next generation weather dependent energy resource integration, right? This is because if you have now, you can coordinate demand response with the renewables, right? Renewables when it is not running, when it is running, because many times in the night, I have seen reports that they have to shut down the wind power plant because there is no consumption. Okay. So what we can do, because there is free power there and we are shutting it down, right? Free power there. So a lot of, if I'm right, in Europe, what they did is that whenever something like this happens, they start pumping the water from the downhill to the uphill, wherever you have a reservoir, and then for the hydro, so helping the hydro plant. Okay, I have seen reports that you can create energy storage, purely energy storage, just taking the stones from down of the hill to the uphill. Okay, and then in the daytime you can bring that stone by the trolley and run your generators. Okay, it's not fully functional, but those kind of reports I have read it. So that's how they are utilizing or planning to utilize these free generators, free generation when you don't have the demand. That's the biggest problem power engineer has, right? When you have a large scale generation and demand, right? So that is that time, that instant, and then done, right? So if you use it or lose it, that's the case, right? Okay, so let's take maybe a couple of minute breaks. So whatever time you have, 10 more minutes add, and then we'll come back and start talking about this one, okay? So I think, so let me stop sharing and then 10-minute breaks, okay? Okay, we can take 1 or 2 students and learn their research. Okay, by the time all the students are coming back. Let's see. Okay, we can talk with Vaisali Tayan. Vaisali? Okay, Vaisali is not there. Okay, we can go with Nitish. Nitish, are you there? Okay, Nitish is also not there. Okay, looks like it's gonna be hard time to find someone. Pavitra Sharma. Pavitra, are you there? Okay.
Let us talk to Madhumati, ETI principal. Madhumati, Madhumati. Madhumati, can you talk about your research work?
Yes, sir. Yes, sir. Tell me, sir.
Yes, please, Madhumati.
So I'm recently working on, I already spoke to you, sir, regarding my work.
Okay.
I am working on decentralized control of DC nanogrids using solar power.
DC nanogrid. Okay, very
Yes.
good. Thank you, Madhumati.
Has Priya Kumari spoken?
Yes, ma'am, I have already spoken.
Okay.
Then we have.
You can take one more, Dr.
Good evening, ma'am. I think you called my name.
Okay, Pavitra, I think that's good. Okay.
Yes, yes,
So,
sir.
so
I'm a
tell
research
us
scholar.
Okay.
Working in BITS Pilani.
Okay.
Yes, basically my research is related to energy management and microgrids.
Microgrid energy.
I am
Very
working
good.
on optimization side, basically.
Okay, okay.
Yes, sir.
That's a good topic. Okay, I think probably we may have something in optimization. We may have today. Okay, so we'll see. Okay, then. Thank you very much. So let's come back. I think this is maybe 1 more minute we have, but let me start this almost. But anyone wants to speak? We have 1 more minute because I said 10 minutes, so we have 1 more minute.
Shihabuddin, can you speak? Shobik Mandal. Swati Krishna.
Okay. Okay, that should be okay, Dr. Prerna. Thank you very much. Okay, so let's, so this is a lot of things demand response can help us, okay? So then next question comes in how we can do it, right? So one way from the utility perspective, okay, that is a volt var optimization, they call it, okay? So it's just definitely a demand response, okay? So technology and infrastructure upgrades integrated into the electric distribution system to optimize voltage levels. By optimizing the voltage level, you can get the demand response, okay? So this is, if you see this green one, that's the historic voltage range, okay? So this is voltage here, 120, okay? What is the voltage in India? We have 220. What is the voltage that we get in our house? Anyone?
230 volts.
230 volts. Okay, so here we have 110, 120. Okay, that's our voltage range. So that's the voltage range, 5%, right? 5% from that nominal values, plus and minus. But VVO means volt var optimization. We can manage to stay in this range. Okay, almost a lower side of the voltage range, basically. Okay, and by doing this, we can significantly get the demand response. Okay. How we can do it? So utilize communications and computerized intelligence to control voltage regulators and capacitors on the grid. So available resources, okay. And again, if you don't have measurements, so you have to have these systems, okay. There are vendors that supply this kind of devices. that you can install, and as a utility you can install it and get the demand response. Okay, again, to mitigate market power, to help the system economically, to help in the emergency responses, that is a good thing to have for the, instead of shutting down the loads, right? So this VVO optimizes voltage and power factor based upon selected parameters. What is optimizing? Voltage and power factor. Okay. Algorithm uses end of line monitoring feedback to ensure minimum required voltage. So what it means end of line is something like this. So think of having a 230 volt voltage here. Okay. And this is a feeder, simplistic view of here. Okay. And you have load everywhere, you have load here, right? So, and when you change here anything, so let's say first one is the black line here, right? So if 126 is the voltage at the substation, you will have the voltage here is 100 and maybe 18, something like that, right? So this is the operating range, 114 to 126, and it compliance with all the standards, right? So between 5% range, 120, right? Then you have this orange line. So now if you change the substation voltage to 100 and looks like 24, right? You are still within the limit here. If you change the voltage here to almost near to 120, you are still within the range. And by, so now you have here, right? Blue one, red one, probably these are the regulators and capacitor banks, right? So if you see here, you are bringing in for the last one, right? Last voltage graph, you are bringing in some kind of control devices. You are shooting up the voltage so that you will not violate the end of the line voltage. Okay, so that's what it means. Again, you need full picture, right? Full communication. You don't need exactly what's going on, but at least get key points, all the measurements you need, okay? So that you don't violate the end of line voltages. So by doing this, what we get, okay? So that is one report that I pulled it off from. This is APRI, okay? And this one, it's saying input real and reactive power as a function of applied voltage for motor. Okay, so we are changing applied voltage, and so how much this motor is consuming. Why we do the study for a motor? Because all the loads that we have trouble with, right, for voltage is all rotating loads. Okay, if there is a blackout and all the motors are connected, okay, and when we are bringing back in the power, that's the biggest challenge, okay, because they are, if you remember from our bachelor degree, that motors takes double amount of power for a half a cycle or 1/4 of a cycle when you are starting, right? And then probably you have done some experiment with starting a motor, right? So there are, means older motor, newer motor comes with that kind of capability. But what here they are suggesting is here means kVAR, so rated voltage. So you can by changing, right? So here, see what is happening here: 100 volt to 130 volts. Okay, and then they are plotting real and reactive power consumptions. Okay, for different voltages. So what they figure out that you can reduce the consumption by about 8%, okay, operating this motor at 115 instead of 125 volts. Okay, so 8% reduction. So that's a very good demand response, basically, right? So you are not shutting down the motor, you are just lowering the voltage. So by lowering the voltage from the utility side, you can get the demand response. Okay. Some statistics I pulled out from one of the NEF's conferences that we organized. Okay, this is in AMI, so 130,000 meters installed in AEP, Ohio. Ohio is a state in United States. Texas is a state. If we have some timeline here, 1 million smart meters, okay, installed, started in 2010 and completed in 2014. Probably in India, we can do much faster, okay? And we have a lot of people if we want to do this kind of thing. So different, so AMI lot of then volt var. So they have also implemented this volt var optimization. So biggest push from the federal level for the demand response, right? How we can leverage. Okay? So many places, right? You can see here Oklahoma is a state, right? And then Ohio is a state. So several. So 17 circuits. Okay, 17 circuits. They have installed 160 circuits are planned, right? So probably by now they might have completed this VVO optimization. Okay, this is classical example, and many events are happening just because of this. Okay, so 10 years back, we had, let's say we have a very long transmission line, 200 mile, maybe 300 kilometer approximately, right? 320 kilometers, right? So that is, yeah, 320 kilometers. Now, and you have a large load, maybe a New York City or maybe a Bombay, right? Some bigger city, large load here. And now this load is increasing. A few years down the road, this load is going to consume 140 megawatt, right? And you don't have this infrastructure. So you have to have a line. You have to build a line from the generation to the load center, right? And a lot of politics, first of all. And after politics, whether you have, because you need to acquire land, it's the biggest problem in United States. Biggest problem, if it is not very well planned, you have to wait. If someone decides that I don't want to sell my land, okay, and that land is important, large land, then you have, means federal government has to put more money to go around that land to build the line. Okay, so very big deal to have a man. If it is multi-state, right? If this line is going through multiple states, then just a nightmare for whoever is building it, right? So the easy option is to have some kind of microgrid, some kind of demand response, some kind of solar, wind, other distributed resources. Okay, so that was the initially push. Okay, so that we can defer. Okay, we cannot defer forever, but at least we can defer for maybe a couple of years, right? So then they installed this solar, wind, and created this kind of responsive system. Now, lot of stress because of that, right? We don't have enough control, real-time control, and then because of that, and a lot of renewables, weather dependence, and then we are going to have some kind of smaller events, disturbances in throughout the grid. And I feel that is one of the reason. Remember, I showed one of the slides that in 2020, 328 larger disturbances were reported in the United States, okay, and about 7,000 in India. Okay, that was the report that I so yes and no, right? It means when you have to build it, you have to build it. I mean, now there is no way you can sustain it. You have to build a line. But yes, for a couple of years, for sure, you can defer by having some kind of these new technologies, communications, renewables, demand response. Okay, 1 second. In cold, it's not yet fixed. Probably you might have already read the slides. Microgrid. Okay, so what is a microgrid? Definition from the Department of Energy: a group of interconnected loads and distributed energy resources, any distributed, with clearly defined electrical boundaries, that acts as a single controllable entity with respect to the grid. Okay, connect and disconnect from the grid to enable it to operate in both grid connected or island mode. Okay, so any grid where you have renewables, okay, and you can connect and disconnect, okay, from the main grid. Okay, that's a kind of a microgrid. Okay, Microgrids are low voltage distribution networks comprising DGs, storage devices, responsive load that can operate either interconnected to the main grid or in an intentional islanded operation. Okay, intentional. Modeling, many of you are doing it, steady state modeling. Okay, control operation, power quality, right? Islanding, supply and demand, communication between different power components, and most importantly, voltage and frequency controller, right? Different control architectures for the microgrid: centralized architecture, distributed management. Sorry, in the centralized architecture, you will have distributed management system, microgrid central controllers, micro sources controllers, load controllers, decentralized architecture, distributed control. Okay, so centralized architecture, decentralized architecture, AC/DC. I think I have not mentioned of AC/DC microgrid. Some of you are already working on it. Okay, so that's good thing. Energy management in microgrid. Again, some of you are working. That's good thing. Microgrid modeling and simulation, DG and grid models are needed. Okay, and has been a lot of research has been done. Okay, so I was I think almost 6 years I was chairing microgrid control task force. So every year we had 30-40 attendees for several years discussing challenges in the microgrid. Okay, various microgrid configuration possible. Consumer microgrid, right? Single consumer with demand resources on consumer side of the point of delivery. Community microgrid, multiple consumer with demand resources on consumer side of the point of delivery. Local objectives, right? Consumer owned. Then you have utility microgrid, supply resources on utility side with consumer interactions. Utility objectives. Microgrids are local energy network. Okay, so now probably it's good question for you, right? Whether when you say microgrid, so some of you said I am working on microgrid. Are you working on which microgrid? Are you working on a consumer microgrid? Are you working on community microgrid? Are you working on utility microgrid? Okay, then everyone has a different models, right? Different objectives. So you have to be sure what you are doing here, right? And there are other possibilities. Commercial parks, industrial complexes, port stadiums, okay, municipality, military facilities, right? Biggest one in United States, a lot of emphasis on military facilities. Okay. Utilities, isolated communities, right? Very far village spaces, right? Very far in where very far that you can't reach, right? Where, but you can in hilly area you may have some kind of solar and wind, good solar and wind. Then you can have isolated microgrid. Okay. Microgrid possibilities in US, right? So we municipalities about 1,300 in the US, 961 under 300,000 residents. Out of this, 961 has 3 lakhs, less than 3 lakhs residents. University campuses. Every university campus is a good place for the microgrid, making it a microgrid. Any IITs, right? Any IIT campus, I think you can build a microgrid. Okay. Military facilities, 440 facilities worldwide. Okay, so every facility you can have a microgrid. Industrial and commercial park, right? And 15,000 in US. Capital cost can go from 10 million to 100 million. Okay. Utility with special needs, so some rural electric cooperative, municipality, or investor-owned utilities. Okay, this one is 27. I think there is one more out. 2018 is out there, but it is showing the number, all the numbers where the microgrids are planned or they are working on it. Okay, building it. If you see in somewhere in India, we have like 19 microgrid in that time. Whether how many really happened or not, that I don't know. And the United States, see, we have 82 here, this side, eastern side, western side, we have 56. Okay, a lot happened in the Hawaii Island in US. Okay, lot of renewables. Okay. General microgrid, so many things, so many problems, okay, so many aspects that you can think of in your research, right? So you have in EV charging, and then smart houses you have, right? Intelligent transportation, vehicle centers, right? Controlling charging of all charging stations, right? Like bus stations that we have, right? So if we can make electric buses, think of it. This one is solar buses, and those kind of biomass, right? Smart buildings, right? Control center. Then we have multi-energy stations where you have solar, wind, biomass, everything together. This one. So endless means right now we have not converged what is the exact microgrid. Okay, we have not converged. But here, typical definition from the APRI, okay, Electric Power Research Institute. Okay. It's very similar to DOE, a group of interconnected loads and DER equipment and devices within defined boundaries. Okay, that's microgrid definition. Acting as a single controller entity with respect to the grid and able to connect and disconnect. Microgrid, if it is not isolated, then yes, you can do island, non-island operation, right? Grid connected and off grid. So here's key figure, okay, where we are saying microgrid, right? So you can have a microgrid single customer and their renewable sources. So this is single customer microgrid, call it, right? And then you have a multi-customer microgrid, so they are communicating, right? So if you see, this is orange color, right? Light orange color. So you have multiple houses, right? It's a multi, and then this one is feeder level microgrid, right? We have, right, small community, right? So this one is feeder level microgrid. So you can have different. So now whether you are working on single customer, multi-customer, feeder level microgrid, right? Consumer level. So now these are the questions probably you should be asking yourself, okay? Now design, right? This picture tells a lot about the situation. Okay, this is in Hoboken, New Jersey, 2012 Hurricane Sandy. Okay, and created this disaster for the power utility. Okay, so when you have microgrid, you can protect, right? You can disconnect, and at least wherever possible, you can supply the power. If you don't have the microgrid, so microgrid is one that it gives the resiliency. Okay, but let's see what we have here. So decentralized ways were investigated to manage many distributed energies and enhance reliability and resiliency. Microgrids, this new grid architecture known as microgrids, enable local power generation to provide the local demand. Right? Microgrids can work in two operating modes, island and non-island, grid connected, right? Advantages of the microgrid. Microgrid support integration of intermittent energy sources and get backup from battery storages, right? Microgrids are resilient against natural disasters, right? This is one of the example, because they can autonomously operate and do not rely on the main grid. Microgrids are flexible since they can provide electricity to remote loads or communicates. Okay? I think there is a company in US, they say, give me $650,000, $6 lakhs, and then you will never have to worry about power. Okay, so you will install everything and then you will have supply forever. You will never have to buy power from the electric utility. Okay. Challenges, okay. Efficient and effective integration of electric vehicles. Okay. Increasing deployment of electric vehicles in the grid, right? Developing the EV battery specifications, example, enhance energy density, vehicle to grid capability, for the, so electric vehicle can act as a generator as well as act as a load, right? Stochastic, I think we done some stochastic control. Stochastic control of islanded microgrids, including renewable energy sources. Okay, mostly our students. Okay, student works very hard. Okay, and definitely faculty also work hard. Okay, but it's all when something really happens. Okay, that is all students. So I don't want to take any credit for that one. Okay. Addressing the air pollution and climate changes issues arising from fossil fuels, right? Intermittent and uncertain nature, right? Stochastic, right? That's the stochastic part. I think we applied different control, okay, to control the grid, basically, okay. Resilient control of islanded microgrid against cyber disruptions, okay. Hierarchical control strategy can be equipped with cyber interface and measuring data. New paradigm of microgrid, so-called cyber physical microgrid, is vulnerable to different types of cyber attacks, cyber intrusion. Designing a resilient control is vital for microgrid. If you see here, this is electric vehicle, I think, prediction. So by 2030, different prediction, we will have 200 million electric cars in the world. 200 million electric cars. Okay. One thing that we did is parking lots in microgrids. Okay, so location, determining the location, where should be the parking lot. Okay, so EV integration to microgrids has three main concerns, right? When EV's battery must be charged and discharged. Okay, if EV is charging and discharging properly scheduled, it can smooth out the daily load, right? Here we are saying this is load curve. Okay, so charge, discharge, so smoothing out this one, charge and discharge, okay? Or probably reduce the peak load. Okay, so if we supply here EV we can use, then we can reduce the peak load. How can EVs travel inside a microgrid be analyzed and modeled, right? How we can analyze, very important. Transportation aspect is important. Applying stochastic methodologies are recommended because of uncertain nature of EV trip. Okay, that's what we are recommending. Where EV parking lots must be placed in a microgrid. Okay. Also, we find the optimal place of EV parking lot to optimize distribution grid concerns. Okay. So these are some of the questions and challenges for the parking lot. Definitely optimal charging and discharging schedule for the EV aggregators proposed methods, right? So here we have this proposed. What we are doing here is to model the uncertainties of vehicles travel during a day. A truncated normal distribution function is used to limit the range of random variables. Okay, so we use this function. Okay, and we did a sequential Monte Carlo simulation. And is applied to stochastically model the EV traveling. Okay. Assumption that we took, EVs traveling is between residential parking areas and administrative parking area, means work area basically. Okay. Some of the lower and upper bound assumption of traveling models, right? Traveling distance considered, storage capability of battery considered, commuting time, forward commuting departure time, working time. Okay, those are the things that we consider here. Very small case. Mean and variance of electric vehicle travel characteristic. Okay, departure time, parking period. Okay, commute time, travel distance, right? Variance. These are the variances. Okay, then we consider the storage here. So again, it depends what you are considering, what is your load. Okay, again here, okay, I'm not going through this flowchart, but we have a fitness function. I think we use a particle swarm optimization algorithm that is available in MATLAB. Okay, and we also added a constraint for the state of charge. And we had constraint for charging constraint, discharging constraint, and state of charge constraint here, okay, on our electric vehicles. Now here, if you see the red line is for residential parking, right? So then basically about 8 to 10, most of the people go to work, okay, and between 4 to 8, most of the people come back to home. And this is the charging, non-residential kind of administrator charging, okay. So number of PVs, different PVs, right? And then we have here exchange power from residential parking and exchange power from non-residential parking, right? So this is charging and discharging kind of. We consider 24-hour load profile, we consider 100 vehicles, and we consider 2 types of area, right? This one here. Okay. So based on that, here based on this function, right, fitness random variables, we created a pattern for 100 vehicles, okay. So charging state of charge basically, okay, for those vehicles, okay, percentage of SOC for all 100 vehicles, okay. So this is kind of utilizing this and doing Monte Carlo simulation. And this is load profile for 24 hours and modified load profile, okay. So that is the black color one, and then modified load profile, okay. And different objectives we consider for doing the optimization. Fuzzification, if you have learned about fuzzification, fuzzy is something that if you are sending, right, and if something falls on, just your body reacts and you move, right? That's called fuzzification. If someone is falling and you say, oh, somebody is falling, right? So that's kind of fuzzification, and it is model like this in these equations, okay. So we consider voltage unbalance, we consider here, so that's the equation for the voltage unbalance. We consider power loss, okay, in the system, okay, and the fuzzification, and definitely fitness functions, okay. Those are the things. And we use available MATLAB IEEE 13 nodes distribution grid, okay, available 13 node grid we consider, okay. And then we say that these 3 nodes in IEEE 13 node. I think probably if we get time, we will do that in OpenDSS, at least model that one distribution grid. And then these are the nodes we consider, those are the administrative buses, means the work location basically. Problem solved using 3 methods. Single objective, that is we just consider voltage unbalance, okay, and then what we are going to get, okay, when we just consider power loss, and when we consider voltage unbalance and power loss both, okay. So here basically, if you want to see that one, so 100 vehicles, right, and then these are the locations that we are considering. So we are just, I think we are not considering the discharging, we are just considering the charging, right, on this one, in this problem. So when we are charging, what will be the impact on the grid, okay, and what will be the losses on the unbalance as well as losses, right? That's we are considering. So we are putting those load profile on each load for that PHEV, right? So, and you can consider something like this. We are modeling that on this one. Okay. So, and I think details are available. We have this published paper, that one. So if you want to know more details, because I don't know exactly, means if you ask me how, then probably I may not be knowing, but the overall why probably I should be able to tell, okay, if you ask me. Simulation results, residential parking lot, okay, so single objective, voltage unbalance, came up with that we should have a parking lot here, 633 at in power loss 646 came out, and in multi-objective residential parking laws were selected as 646 location, okay. And when we say this number, so this 13 node has different node numbers, okay. So these are the node numbers on the 13 node system. Okay. If you are familiar with, if you are worked on it, probably you know what I'm talking about. If not, then we are going to take an example of 13 node system, okay. At least we are going to run a power flow on OpenDSS. hopefully. Okay. We still have a lot to talk about it. So administrative parking lots, when we ran for those nodes, right, voltage unbalance, this was the best node. This was the best node for the power loss, and this was the best node parking lot, right, location of the parking for administration. So we are choosing one location. Okay. Probably if other buildings will complain why you are installing here, right? Because we are solving the problem from the power grid side, right? We are not considering what will benefit, means what is easier way, what are the available buildings, right? Those are the things, other aspects of it. But here we are just considering the power side. Okay. And objective voltage unbalance, we got the objective values is 25 point here, then 25.23, right? So very similar for multi-objective, is very similar to this value, right? Very similar to this value. Power loss, the objective without EV aggregator, this is value we are getting. Okay, so this is the minimum value we are getting. Okay, so minimizing, right? We are optimizing, so minimum value. And here, single objective power loss and multi-objective, we did not get any much difference. The problem is smaller, remember, just 100 vehicles. So suggested parking lots for both single objective algorithms are different, right? Each of the single optimization algorithm has one mutual suggested parking lot, right? So this one here, out of these two, 640, so still it is pulling up good number. Out of these two, multi-objective is pulling up 633. So it's still not choosing different one, the third one that we have. Okay, so this, we can say that our algorithm kind of working. So we did this one so we could run this whole simulations in a kind of a Monte Carlo way. So black box simulation, we could do this one and record all the data and then doing the optimization on this one. So every time we get the results, we run this simulation through black box kind of. So probably if you have worked on it, MATLAB, so from the MATLAB program.m file, you can run the simulation file, okay, and get the results what you need into your .mem file. Probably you already know this is classical conventional generators, right? Very nice output, okay. And then if you have solar and wind, not nice, right? So this one is 0.5 megawatt, 2 megawatts, such a large spike, okay. But if you think about this one, and if you think about the loads also, load pattern, it will match, right? Loads are also like that. It means any house, everybody is switching different time, everybody's freeze is switching different time, air condition is switching different time. So you will have this kind of spike in load as well, okay. But the load curve and your solar curve, their peaks are at different time, right? Solar in the afternoon and in load peak is about generally in the evening, right? Early evening. This one. I think now we have one journal papers on demand response. Okay, so I think I extracted that some of the information on that one. Okay. So demand response modeling and its impact on IEEE benchmarks network. So we use IEEE 8500 node system to do this demand response. Okay. Market optimization model for an islanded microgrid that includes various smart grid elements, including demand response, distributed energy resources, and battery storage. Okay. Objective, optimum generation and demand response level for islanded microgrid market using linear programming. That was the objective. Now, demand response, we know what it can do. Okay, so what kind of demand response are here in the United States? Okay, so different demand response program, like we already mentioned that about 32, I said, right? Gigawatt of demand response was achieved in 2018-2019 time. Okay, so direct load control for the industrial customers, interruptible or curtail services, right? Demand bidding or buyback. Okay. And emergency demand response, capacity market program, time-based. I think in our program we use real-time pricing signal. Okay, or day-ahead pricing signal, time of use, real-time pricing, critical peak pricing, right? So different for the residential customer, different programs. We develop price elasticity metrics, okay? And we'll talk about what is price elasticity metrics, okay? So price elasticity metrics is developed for a day-ahead real-time pricing scenario, okay? And that is, one is self-elasticity coefficient, that is represented this one. So this is D for demand, P for power, and E is the value, okay? And the cross elasticity, so I think it should be here EII, I think. Okay, so self elasticity is same time for the same load, okay? And cross elasticity is different time, okay? So self elasticity is a measure of load curtailment by the consumer, where a cross elasticity is measure of load shifting, okay? Load shifting, and at the time you are seeing the price and you are curtailing the load. That's the measure of self. So we build this coefficients basically for each individual load, okay? Supply. So now probably you ask that if you have a million load, right? If you have to come up with million times 24, okay, that's a lot of numbers, right? That's a lot of numbers for this price elasticity. And then we'll talk about how we can reduce that, okay? So assumptions that we consider here is automated meter infrastructure, right? Or smart meters is assumed to be deployed at the customer's premise to facilitate day-ahead real-time pricing signal, okay? So we have a, so the E that we were mentioning, so this is the E value we are plotting here, right? So E for one of the customer, okay? E value. What is self-elasticity? Curtailment of the load by the consumer at that time when they are just seeing the price, okay? Oh, this is so much cost, and then we should just don't do that, okay? Let's not turn on our washer or dryer or that, okay? And this is the price, real-time pricing signal, okay? That is cents per kilowatt hour, okay? So we divided the consumer in 5 categories, okay? So like I said, million, just impossible. So we divided consumers on 5 categories. One is long range, where very advanced, I would say. This one is consumer that it can plan for 24 hour based on the price signal, okay? So that is, so it can shift the load during that 24 hours time. So long range consumer. Short range consumer that can't plan 24 hours, so maybe 10 hours or 6 hours, okay? So that is short range consumer. Then we said real world postponing. So they can, these are the customers, they can postpone the load for next 5 hours, okay? Within any next 5 hours. Real world advancing, that is past 5 hours, okay? So because they ahead fine, so they can, if they are planning to turn on their washer at let's say, or dryer at 9 p.m, probably they can now do it at 4 o'clock or 5 o'clock. Different schedule, right? Everyone is different, million possibilities, okay? So we just created this kind of behaviors of the consumer, right? Modeling real world mixed consumers, so they can, from the current time, if they are operating at 4 o'clock, they can go 5 hours back or 5 hours forward, okay? So these are 5 categories, 5 behavior. We have a model for demand response, basically, okay? And for this 5 consumer, we build this elasticity matrices, self-elasticity, that is row and column, like diagonal elements are self-elasticity, and the cross diagonals are cross elasticity, sorry, off diagonal are cross elasticity values. So we build this one for those 5 types of customers, different types of customers. So and we are not showing, due to the space, we are not showing all 24 by 24 matrix here, okay? Similarly, for real world postponing, okay, these are the values, okay? And real world mix, these are the values for the real world mix customers, right? And I think now I have the right values here, okay? PMs have been used to compute mathematically the level of DR, right? per customer type. So these are the self-elasticity matrices or self-elasticity. Okay. So how much price change, how much load is going to change. Okay. How much price change, where is load is going to that same instant of time at 2 o'clock, right? And this one is, if it is 2 o'clock price change, where you are going to shift the load. Okay. Yeah, you are planning to shift early of the time, later of the time. Okay. So that is cross elasticity. Okay. And based on that, we build this load curve for that consumers. Okay. So self elasticity, we already write this one, right? Talk about it. And we consider this IEEE 8500 node system. In this one, we had about 1100 to 1200 residential customers. And so that was just beyond, this one is the master project. Okay, that was just beyond our capability at that time. Okay, now I think we have the capability, we can do it even for 1200 customers. Okay, so we consider this part of the feeder, means we consider about how many, 245. Okay, so 245 individual residential load, we consider this the loads at this feeder basically. Okay, this section of the load, this section of the feeder we consider, and we build those matrices. Okay. So we did a time series distribution power flow for 5 different scenarios. Okay, in OpenDSS you can run time series distribution power flow. Okay? But one disadvantage that it just stores, it won't give you every single time instant power flow results. It will just gives you the best and worst results. Okay, what are the least voltage or what are the maximum voltages that power flow has seen during that 24, means whatever the time that you are considering. Okay, and if you need that for every single moment result, then you need to use OpenDSS MATLAB interface. Okay, so you run the OpenDSS like a black box from the MATLAB. They have, again, it's almost a lot of learning time on that one. Okay, we had a hard time figuring out running MATLAB for OpenDSS from the MATLAB, running OpenDSS from the MATLAB. So one of our PhD students did that one. Okay. Okay, scenario 1, no demand response. Scenario 2, loads of the highlighted sections model as long range customers. Scenario 3, short range customers. 4, real world mix. And 5 means mix of all these customers. Okay, so 5 scenarios we consider in this one. These are the results for that sections. Okay, voltage profile. If no demand response, we see some violations on the voltage. So that is this case, black line. And with demand response, we can basically improving the voltages with demand response for different. Okay, a long range consumer, okay, is basically is giving us better voltage. Mixed range, the worst one is the real world, right? So real world consumer is still helping, but it's not better than. So best customer is our long range. Okay, because we are deciding those pricing for helping our network, right? So if someone is going to utilize that pricing signal and doing best to optimize their load, taking full advantage of it, the utility is going to get the most benefit, right? Utility is going to get the most benefit. Okay. Voltage analysis results, right? So this is without demand response, okay? And this with demand response, okay? So this one is voltage analysis results here. What was here we got here? So this one is also voltage analysis, okay? This one, voltage analysis here, okay, during off-peak hours. So these are off-peak hours that we have, and these are peak hours that we are getting, okay? So losses, of course, when your customer is long range, okay, you are going to see good amount of loss reductions, right? When you have no demand response, your losses are high. When you have the best demand response, your losses are low, and in between, right? So that's what it is showing here. So this axis is 1 for long range consumer and 5 for no demand response. So long range, short range, real world consumers, okay, and then losses it is showing. This is for peak pricing hours, right? This one is for during off-peak pricing hours. Okay, so different losses it is showing here. Loss analysis, zone losses in kilowatt hour. Okay, for various demand response scenarios. So this one is peak pricing hours, off-peak pricing hours, off-peak pricing hours, and definitely with demand response we have much lower losses compared to no demand response, right? So demand response. We also did a multi-agent on this one, okay, coordinated control on this one, okay. And this is the, we did it on, this one is, we received a model from American Electric Power. This is 650 node circuit. Okay, and then we consider applying multi-agent system here. Okay, so we model this in OpenDSS, this 650 node. We'll talk about it probably today. Okay, and so no demand response with VAR support, and this demand response for VVC. So this one before VVC was even came into existing. Okay, so this is long back we did this one. Okay, so we showed that with VVC you can do better, right? Better demand response. Okay, I think I need to take a break. Okay, so give me like maybe 10 minutes and then I will come back. Okay, and if Dr. Prerna is available, you can share your research by the time. Okay, so I need to take a 10-minute break and I will come back. Dr. Prerna, are you there? Sorry, I'm just calling you out of blue. Okay, so probably if Dr. Prerna will come in and then you can talk about your research. I need to take 10-minute break, okay? Thank you very much. Hey, sorry, I'm back. I had to run out. Okay. Thank you very much. And let me share my screen. Okay. So distribution system, a little bit about distribution system now. Okay. Distribution systems, definitely kind of a substation. Once we have a transmission line comes in, substations, right? And substation transformer here, we will have some voltage regulators, 3-phase lateral, single phase lateral, right? And then you can have a V-phase lateral, okay? Kind of. Then you have a capacitor bank, underground cables, right? Inline transformer, different configuration, Y delta, distribution transformer, and the set of customer loads. So, right, lot of things in distribution system, and all 3 phases, and then unbalanced, right? So this loadings are unbalanced, okay, in distribution power flow, right? Non-equilateral conductor spacing of 3-phase overhead and underground lines, how we can model it, right? Very important one. High R by X ratio compared to a transmission system. In transmission system, your X by R is high, and distribution R by X is high, okay? Distribution system is ill conditions, and hence the fast decouple method is not suitable for power flow system. Some probably may converge, but in general sense, fast decouple method is not suitable for distribution system because of R by X ratio is higher, okay? Constant power demand does not hold good in distribution power flow, okay? Iterative method must be employed for solving power flow. Most widely used in forward backward in open DSS, and I think Grid Lab D, if you have not heard about that software. Those are the 2 software I think openly available, and they use, I think, backward. Open DSS for sure, I know that it use backward forward sweep. Acquire all necessary data, right? That's the challenge. The loads on the distribution system are not constant, and the meter is prone to errors, right? Detailed component modeling is needed in distribution power flow if you want to do it. The impedance calculations of 3-phase unbalanced overhead and underground lines require accurate models, right? Then what we have here, distribution substation, residential and industrial load, distributed generators, okay, that we can model here now. Normal state data, distribution, power flow with DG, data, topology, DG, right? Backward forward sweep that we use, and then we calculate node voltages and branch currents, okay? Restoration, I think we talked a lot about this one, okay? So we developed distribution power flow with DG, okay, during our time. DG placement, once you have distribution power flow, deeper understanding of this distribution power flow, then you can do all these things in distribution system, okay? So power flow is the key. Once you know the power flow, how to do it, and even in United States, we don't have many universities that teach distribution system 3-phase, okay? And I'm sure the same thing in India as well, okay? But once you have the deeper understanding of distribution system and distribution power flow, then you can do like a placement, parking lot placement, solar placement, large scale, utility scale, capacitor placement, large scale, loss reduction, volt var control, right? Definitely restoration and contingency. Contingency is not even doing it. We don't do contingency analysis, okay? But future probably we have to do it. So we, I think, applied our developed distribution power flow on IEEE 13 node, 34 node, and kind of microgrid system, multi system, right? This one. So this one is a SIP system that we work on. This one, and this one, AC, DC, both system. Power flow, distribution and transmission, many people, they talk about microgrid, they talk about distribution system, and then they use balance system, right? If you are using balance system, then it's not a distribution system, Okay, distribution systems are unbalanced. But again, as a student, if you are working on some kind of controls, right, then probably just understanding the control, developing control, three-phase, single-phase should be okay. Okay, but in reality, means if you want to compare reality, then reality is this: distribution systems are unbalanced, three-phase, and R by ratio much greater. Right? So three-phase analysis, unbalanced systems, mutually coupled lines. Okay? In distribution system. So lines are also mutually coupled. In transmission, single phase, balance system, transport line, right? And then component models, load characteristics, large number of branches and nodes. Here, no separate components, generally constant power or zip model we use in transmission system, smaller number of branches and nodes. Condition, not explored, single source, okay, not ill condition, not ill condition, studied for long time, transmission, multiple source, okay. A reconfiguration, you do it for distribution system, transmission system, many objective. You want to do load reduction. In our lecture when we talked about load balancing, volt var support is, you already saw that it's happening everywhere in the United States because there is a benefit. Volt var support, big good benefit can reduce our overall load, okay, if you do it right. And restoration is definitely important as well. Fundamental calculations, steady state behavior in power system. Okay, to understand, to get the steady state behavior, that gives us, power flow gives us that. Okay, power flow can be used to optimize circuit usage, voltage profile, kilowatt, kVAR losses, transformer tap settings, equipment limitations, and economic planning, right? Everything basic is power flow. So as a power engineer, you must know details, and I would recommend that you should program it. So roughly 3-bus system, 6-bus system for distribution power flow as well as a transmission power flow. If you program it yourself, you have the core understanding of power system. Okay, and then you can do all kinds of whatever you are doing. Okay, so as the first 6 months, you learn what are the equations to do power flow. Okay, and then you will be like jumping in the tree basically, because now you have the basic understanding of the power flow. Okay, basic understanding. This is necessary first step in a stability study to establish power flows and machine power angles before the initiation of disturbance. Okay, again, I teach a course on graduate level course on stability and control, 535. Okay, in that one I talk about multi-machine system, multi-machine modeling. Okay, and how the fault means how machine will react when you have a fault. Okay, that one most of IITs should offer, I think, that course. And again, it's a good course. Okay, if you are power engineer, I think again I recommend that course. The study is used for optimization of power system and distribution automation, which needs repeated fast power flow solutions. Right. Distributed generation, DG, small capacity generation installed on distribution side, portable, flexible, diversifiable, controllable, right? Reduce delivery cost and makes more efficient use of grid. Right? That I just showed you the example. When your load increase from 100 to 140 megawatt, so instead of installing a new line, 200-mile line or 320-kilometer lines, can we defer it? That's where the DG help us to do so. Okay, avoid many hidden calls of centralization, environmental and social benefits, black start capacity and spinning reserves can cause reverse current on some lines, many lines now, right? Can energize portion of the system separated from utility and create silence. Unbalanced power flow determines line flow and bus voltages. Non-linear equations require iterative methods, right? Backward forward sweep method is employed in the power flow that we developed. Loads are represented as constant power, constant current, and constant impedance in distribution. Okay, in transmission we have just zip power flow model. Fully coupled three-phase impedance matrix for lines and cables. Coupled means because mutually coupled lines we are considering. Okay, and I think we did study on impact of not modeling and modeling mutual coupled lines. Okay, so there is a small change you see in the voltages with coupled, and but we have not done the study, I think, with the fault, and I'm not sure whether we have done it or not. But in microgrid, it's good to study some protection, right? Some of the protection students are here applying protection. So good to study protection aspects on the modeling of lines with coupling and without coupling, how the protection will change. I mean, is it really going to affect? I think on the boundary side, it may affect the protection settings. Okay, that's my understanding. Switches, capacitor, transformers also model. 4 different types of transformers are modeled. Initialization is not a flat start due to several shifts and transformation ratios. Shipboard power systems are like microgrid sites are tightly coupled. In this case, have shorter cable lengths and are ungrounded. Right. Shipboard power system has multiple sources and can be represented as DGs. Okay. DG can be modeled as PQ node, okay, constant power factor, or PV node as constant voltage. Okay, so PV means P and V constant, right? P and Q constant. This one. Steady state analysis of Healy shipboard power system, IEEE 13 node and 37 node there. System studies on this 37 different models and varying DG penetration we have done. Results we are going to present the results on without DG, with DG, and different models of DG. Okay, we use RDEP that was developed by Custing, Professor Custing, William Custing. Okay, from New Mexico State University. He is retired now. Okay, and he has a book. Okay, and he has given a lot of information on distribution. A company called Millsoft Utility Solutions Inc. He uses in their system. That company uses backward forward sweep in their suites of offering for distribution system. Okay. Radial distribution in SIP system, radial distribution architecture is contrasted with zonal approach. We create here zone, right? Zone 1, zone 2, zone 3, priority loads, non-priority loads. Remember, this is electric war SIP. Okay. So zonal approach, starboard and port main bus, sectioning SIP in electrical zones, right? So left side or right side. Okay. That is zonal. If you are from Navy, probably you know what is starboard side and what is port side. Each zone incorporates 2 PCEM power module, basically distributing power to loads. Okay, the loads are classified as non-vital, semi-vital, and vital loads. The vital and semi-vital loads are provided with alternate power supply from other sources. Okay, in case of failures of both power sources, the DG supplies load within the zones. Okay, so a little bit more detailed view of the SIP microgrid system. Okay, so here you have a vital load has multiple paths. Vital load has multiple paths, right? Non-vital load, these are all non-vital load, only one part. So this is starboard side. Okay, so this is front and this is the back, right? This is port side, right? This one is port side. And then when you model it, you will have a kind of, this is all DC we are modeling here, an AC DC here, AC DC here. So these are all DC, kind of DC microgrid. Good example. If you are looking at, someone said that we is working on DC microgrid, So you can look at SIP system, older papers on DC microgrid. Professor McGrady, I don't know the spelling, and I think it was Texas University, somewhere in Texas. He worked a lot on this SIP side DC SIP system. Okay, so you can look at those papers, read some of the papers for if you are working on DC microgrid. Okay. Okay, softwares, different software provided, but nonlinear system, three-phase, still it's this NP complete problem. Okay, so it's not there. Anytime power system problem is generally NP complete. So when we were, and the optimization is mostly we have is convex and non-convex, right? So we have to make our problem like solvable. Okay. For the optimization perspective. So NP problems, so any power problem we have to convert to non-convex problem to convex problem, or our power problems are non-convex problem, we need to convert to convex so that you have some kind of solution and search space for the optimization to solve for it. The snapshot of RDAP, but we can consider OpenDSS. We'll talk about it, this one, but the OpenDSS uses the same thing. So this is kind of a modeling we are doing for the distribution line. Okay, and then coming up with this model, how far from the ground, what are the distances between A phase, B phase, and C phase. And based on that, you can calculate your Z matrix for this one. This is mutually coupled. Okay, if you don't have you have some researcher just model ignores this mutual coupling because it's complex when you want to do decouple control. Right, you won't be. It's very hard to decouple this kind of a complexity in the Z matrix. Okay, so then you just model. You ignore this off diagonal term. You just model the diagonal term. When you just model the diagonal terms, you are basically decoupling. Means you are ignoring the mutual coupling effects on the distribution system. Okay, so I would not recommend to do that when you are doing protection. Okay, but yet to be seen. I am not expert on protection side. This one is IEEE 13 node data. So I think we will go through this data, okay, on OpenDSS. Okay, once we take break, we will start working on that part. Okay. 37 data that we model this in. We develop MATLAB based power flow that specifically works on 13 node and 30 nodes. Is not generalized. Okay, not generalized. And then you can model this microgrid system, SIP system as well.
Excuse me, sir. Excuse me,
yes.
sir. What is phase 4? In the previous slide, you have shown the data. It's written phase 1, phase 2, phase 3, and phase 4. The spot loads. In the table, spot loads.
Okay.
Next slide. Next 37.
Okay.
Yes, in this slide, in the table of spot loads, you have written load phase 1, phase 2, phase 3, and last one is phase 4.
Okay, good question. Let me see.
Phase 3, next one is phase 4.
Okay. See here, this is 37 node system, right? And if you see here, these are all the loads are delta connected loads.
Right.
Okay. So it's not phase 4, it is phase 3, phase 3.
It's phase 3. Okay.
Yeah. So like A, right? A, B, B, C, and C.
Right.
That is okay.
Just missing.
Okay. Okay. So these are all delta connected. That is why we have that. Okay.
Right.
But good notice, Manbir, that you good catch on that. Phase 3, it is phase 3. But we in United we have, I think we have 6-phase system still in existence somewhere in the California. 6-phase system, okay, and if you think about, if you are a machine person, you know that you can have actually 360 phases. You can build theoretically or practically 360 phase system. Why they came up with only 3 phase? You can build 6 phases, so you can divide 360 by whatever number, right? It means if you get the unit number without decimal point, that many phases, you can technically have it and build it. But 360 lines is just too much, right? So they came up and they settled down on 3 phases. So there is a lot of discussions and that one as well.
Right.
Yeah. Okay, so little bit on the modeling side. Okay, forward sweep. So these are the equations for this forward sweep. So basically on distribution side, you start with the lowest point on your distribution grid and you start calculating upward. Okay, so you knowing this voltage, you calculate this one. Okay, so I plus 1, you calculate this one, Z, and I plus 1, calculate this one. So you know your distribution line impedance, you know the nominal voltage, you calculate the currents of the load, okay, and then you calculate the bus voltage, node voltage. Similarly, for the transformer, in transformer, you need to have this matrices, how your transformer is connected. Y delta, delta Y. Based on that, this A and B and D will change based on how your transformer is connected. Switch, open or close, right? Simple open and close. Backward sweep. So in the forward sweep, you know basically source voltage, you calculate the downstream voltage. In backward sweep, you know your downstream voltage and you calculate your upstream voltage, okay, substation voltage goes towards that. Similarly, these are the equations for the transformers, equation for the switch, and modeling for the DG, distribution power flow. Okay, what we did here is distribution power flow. This was the critical point here, okay, because when you are modeling DG, your DG always have a balanced internal voltage. But where in distribution system your DG is connected, right? That node chances are that will have unbalanced voltages, right? So when you have unbalanced voltages, balanced voltages of the generator, how you are going to inject it. So these are the details of those injections. So when you model, generally you inject the currents from the DG, okay, how much current you are injecting on this one. And the critical part is calculating this Z. So Z has to be calculated from the DG to the source, all the Z's, okay? Then only you are properly injecting your current. So that's the big challenge of calculating, okay? But if you can just do PQ model, if you probably PV model, you will need this Z, but PQ model just negative P and Qs would be sufficient for the DG model. Load model, okay, so these are some of the equations for the load models, okay. Now, constant PQ is easy, right? Constant PQ means knowing your P, and so whenever if you are doing any simulations, you will see a load model PQ, right? So you just provide P and Q information, A, B, C phase, remember, okay? So you are calculating for each phase is this one and each node, right? So knowing PQ and nominal voltage, knowing PQ and iteration process. So you start with the first nominal voltage and inject the current at that particular node, okay? Then in your second iteration, you come back, your PQ is constant, your voltage is changing with the iteration until it converges. You again calculate, so every iteration you are calculating, injecting the current into the system, okay? Or basically you can think of taking the current out from the system if it is a load, right? So it depends on Y connected, delta connected. Delta connected, that we already saw that A, B, B, C, and CA, right? So constant Z. Now, when we say constant Z load model is what it means to us, okay? So in constant Z, again, the input is P and Q only, right? So you use P and Q input, you calculate your Z based on the nominal voltage. Okay, so now first time you calculate and this Z value remains constant throughout the iteration. Okay, so but then you are calculating the current, keeping this Z constant, and whatever the voltage is changing in your iteration in distribution power flow, this voltage is changing in each iteration, and then your current is injecting or taking out from that is changing. So that's the constant Z model. Okay. Similarly for the delta, instead of this, you will be line to neutral. You will be using line to line voltages. Okay. Constant I, how you model the constant I? So you calculate current PQ based on nominal voltage, okay, and then you are changing the voltage very similar to this one, but current amplitude remains constant in this one, okay, constant current model. So different model that can be, and then you can have a SIP model, right, percentage. So then you, again, it will be complex if you are really building some kind of microgrid flow, load flow for this one. So depending on what is the component, 10%, 20%, 80%, 70%, right? So for the each load, you have to do all these calculations together instead of separate calculation. Okay. DG modeling, I think we are running out of time for the open DSS, okay? So we'll do maybe 5-10 more minutes and then we'll jump on to open DSS, okay? But here, the DG modeling, I already explained. What we are doing is we are just injecting the right current, okay, on the right current. And a lot of different ways, because we are modeling DG in PQ, like constant PQ, constant PV, right? And then P constant, V changing, V limit that you hit, how you can take care of it, right? Because DG don't have the infinite Q, right? So whatever the Q limit hit, how you handle it, okay? All these things are available in this basically modeling of DG. So once you have all proper modeling here equations, then you have your basically a power flow, a complete power flow. So we compared our MATLAB power flow with the power flow with RDAP. Think of RDAP is very similar to OpenDSA. Okay, and we got a result. And we consider this is a good match. 2 decimal points after the third decimal, we couldn't match it. Okay, so we couldn't get exactly 95828. Maybe some kind of calculations, truncation error, how our MATLAB handles and how the C program or Fortran, whatever they have written, handles it. Okay, or that this one was calculated on different bits. Okay, so that error means we could not this. So I think we consider this is good match. Here we have 3 digits after the decimal, 3 digit after the decimal here also 3 digits. So those are good results. Okay, anything 2 to 5%, 2%, I think 1%, 2% are good result, I would consider. Okay, 13 node results here, all the voltages, branch currents and everything here, but we will work on open DSS on this one. Okay, at least 13 node I have planned that you should get the knowledge and we should be able to run 13 node system. Okay, so this is what we did. This one is I think DG penetration, we varied the DG penetration from 0 to 35%. Okay, and these are the node numbers, different node numbers. Okay, on this 37 node system, right? This one is, and we saw the voltage deviation on this one. Okay, and higher the penetration, right? And so you cannot means what we learned is that you cannot say that DG in your system. Probably I may be jumping a little bit earlier than my discussion, but it depends on the system. Okay, when you want to see whether the DG is helping the system or DG is making worse for your system. Okay, so if utility is not careful and installing solar farm far away from the large load center, then instead of DG helping, DG is going to create problems for the system. So the ideal location is generally the substation. That's the ideal location. Wherever you have substation, that's the ideal, or wherever you have the largest load. Okay, that is the ideal location for solar farm. Apart from that, you need a lot of studies before you really can say that DG is helping my system. Otherwise, when you have a larger load farther from the solar, right, then solar is now feeding that, and you will have larger losses in the system. So that is one hard lesson we learned from our analysis. So again, that is why I say that you have to do, it's nothing for granted. You have to do detailed study. You have to understand. You have to plot. Now at least we have a lot of information. You can plot this, analyze it, do Monte Carlo simulations. Okay, everything, even if you are doing control, I suggest that just do Monte Carlo simulation. Just not rely on one simulation result. Just create lots and lots of plots and see what is happening. Okay, see the overall what is happening. I think you will learn a lot on that one. Okay, 4 more minutes and then we'll take a break. Okay, so these are different studies, different cases we consider from case 1 to case 12. We increase different loading, 5%, 10, 25%, 50% loading increase, and we increase the generation DG to 35%. We model DG as a PQ-PV load, PQ-PV, sorry, node. Okay, and these are some of the results for loss comparisons. Okay, and 10, 11, 12, 10, 11, 12. Okay, so 50% DG, not even 35. Here we are considering 50% penetration. Okay, so again, in this particular case, we are able to reduce the losses, but it's depend what it depends on where is your DG and where is your largest load. If they are far apart, then you are not going to get the loss reduction. You are going to see larger losses. Okay, so anytime as a student, as if you are doing any studies, deep understanding of your network is must. Okay. This is kind of a microgrid or Hilly system, SIF system, power flow with DG. Okay, that this is what we did as a new. Okay, we build a DG models into the power flow at that time. So RDAP was not capable to do so. Means RDAP you can just do PQ model, you can't do PV model. Okay, so that was our contribution in this one. So we model DG as a PV on this one. Okay. Okay, open distribution system simulation. Okay, OpenDS is open source tool developed by APRI. Okay, can do power flow, harmonic analysis also, dynamic simulation it can do, runs annual load simulations along with daily and yearly power flow solution. Now I think it has a capability to run even 5 seconds simulations. So if you have 5-second data, 10-second data of the renewable and you want to see the impact on your grid, you can quickly model it and simulate it. Okay. They provide MATLAB COM interface, so you can run OpenDSS as a black box. So dynamic simulations you can do. Okay, not transient, dynamic simulation. So any demand response application, volt var applications, secondary control, any type, even secondary control. I don't think frequency is a good idea. I don't think you can do that, frequency control in using OpenDSS. And there are a lot of models available, IEEE benchmark. I think our committee, distribution system subcommittee of IEEE, PES is working to create a new model. I think 18900 node. It's work in progress. It's rotated in our group. Those are involved in this distribution system subcommittee. So 89 soon, probably 1 year or 2 years down the road, probably you will see that. Anytime you are working, that make sure that you start with basics. You have solid understanding of basic, come up with some benchmark that is available, that you first replicate that as a student, and then you do your additional development. Okay, just don't go out of blue that I want to do something new. Okay, just replicate outside what is available, that is you can easily do that in less amount of time. And once you replicate, then you can add into it. Okay, that is generally, I would say, for at least for master students or early PhD students. Okay, so it's a good time. Let's take a break and then we will work on OpenDSS. Okay, we wanted to talk a little bit more about microgrid, but I think we covered a lot of things. Okay. So let's take a break, maybe 5 minutes breaks or 6 minutes break, and then we'll come back and then work on OpenDSS. Okay. Let's see. Okay. Let's start. Thank you, Dr. Prerna. Okay, one more thing that I had to talk about. Okay, before we go into the distribution on open DSS. Okay, a small signal stability, right? Microgrid, and some of you are working on microgrid. So I think that's next couple of slides are very important. Those are the lessons learned, things that we have really spent a lot of time on that one. Okay. And learn about it, microgrid. So I think these are very important for whoever is working on microgrid, at least AC microgrid. Stable system, unstable system, right? So now this is a disturbance for sure on the system, right? So this disturbance will create a blackout or not, right? Means whether this whole truck will fall down or not depends on so many things, right? It depends on how fast driver was coming, depends on the soil conditions, right? Depends on experience of the driver, right? And depends the mood of the driver, right? And what else it depends on. So many factors affects the stability of the system, right? Whether really you can either make this system unstable or you can make this system stable. So a lot of factors affect. Similarly for the power grid as well. Okay. So generally, whenever we want to do some kind of stability study, we create a small signal. That is the first step, small signal model. We create our system model. And then there are 10 tools that are generally, we do it is eigenvalue analysis, root locus techniques, Nyquist criteria that we use. Okay, so eigenvalue analysis is generally in our research, we generally use my eigenvalue analysis. Okay. And to understand small disturbances, right? So once you have small signal model, small disturbance, how your system is going to perform. Large scale model, generally nonlinear models, right? Lyapunov stability, extremely hard, okay, extremely hard, very system specific. Simulations, solving nonlinear equations, okay, that's a way to go for large stability. Broadly, stability of microgrid can be divided into frequency stability, voltage stability, right? Frequency and voltage instability can occur due to small or large disturbances in the system, right? Small signal stability, we need a state space model on the microgrid. Okay, so there are a lot of research out there, a lot of papers out there. Okay, the key paper is if you are doing microgrid paper, microgrid research, and if you are working on some kind of control, then definitely you should refer our paper. But what we referred is Bidram. Write down this name, Bidram, BIDRAM. I think it is 2005 or 2007 paper. That is the key paper on the microgrid, Bidram. Okay, we took a lot of from there. It's kind of for us, it was a benchmark paper. Okay, that was a benchmark paper. So for microgrid, we need to model, right, all kinds of control. So each inverter will have current controller, voltage controller, power controller, right? And then you have a linearized unit, you have a nonlinear equation, you have linear equations, right? So represent the system by mathematical equation, right? Linearize the equation, perform stability analysis, right? For any control, generally DQ frame is preferred, okay? And why DQ frame is preferred? I think a control of inverter requires that voltages and currents follow defined set points. ABC sequence of voltages and currents can be converted to DQ signal, okay? So when we talk about microgrid, generally for us, most of the paper that we publish is three-phase microgrid, okay? Following are advantages of transforming signals from stationary frame to rotary frame. ABC are stationary frame. Okay. For balanced circuit, it reduces number of controlling variables to 2 DQ from 3 ABC. This reduces number of compensator to use. Path transformation changes variable to a DC value, which can be easily controlled using PI controller. Okay, so that's you do ABC to DQ frame using path transformation. Okay, control of asymmetrical system is not possible in ABC frame. Okay, state space model of a microgrid can be divided into subsystem, DG modeling, right? Lines modeling and load modeling. And once you have all these three state space, then you can combine and you can have a microgrid model, complete microgrid model. Okay, right. So start with the smallest possible model. Okay. Now this is main aim of power controller. So in this one, so we have a different controller, right? So for DG inverter, we have power controller, voltage controller, current controller. These are the governing equations for the power controller, droop controller, right? And then each inverter, how much is going to contribute with the changes in the power is decided by this coefficient M. Virtual inertia can also be added to the system, okay, by introducing swing equations. Inverters with swing equation in power controller are called virtual synchronous generators. Some of you, I think, mentioned some of you, okay, virtual synchronous generator. Okay. Power controller recent IEEE recent or couple of 1 or 2 back, 1 month back, they talk a lot about controllers, okay, different controllers, frequency controller, frequency modeling of the microgrid, black box modeling they talk about. This one, if you have not studied in your BS machine class, but this one is when your generator is running at a set point, right, set frequency, and then if you don't change this set frequency and you produce more power, your frequency goes down, right? If you want to raise the frequency, then you need to raise your generator frequency, then you can basically raising this, okay? So definitely, otherwise your when you supply more power, you will have a lesser frequency. I'm receiving a phone call. Give me 1 second, okay? I have to take this phone call. 1 second. This is for my daughter. My daughter's doctor is calling. So just give me 1 second and I will be back. Huh? Sorry about that. Hey, please accept my apologies, but here that's how it works in United States. They generally, when you have some kind of referral, they call us, and if we miss, then we have hard time finding that person. Okay, so that is why I had to pick up the phone. So sorry, and it's about my daughter. So I just wanted to make sure. So please accept my sincere apology that I just hang on to you. Okay, so sorry about that. Okay, so similarly so when you want to increase the frequency, you have to increase the set point of the generator, right? And this is for each inverter will be different. Similarly, each inverter is different. Similarly for the voltage control as well. So power controller, these are the kind of state space, linearizing equation, all these details, and a lot of papers of our papers have a lot of details on this one. Okay. Again, this is voltage controller, state space model of that voltage controller, current controller, all the details, all the equations are available here, DQ frame, right? DQ frame. And then LCS filter, modeling again with line modeling, filter modeling, all the ABC, sorry, state space equations you can build. Again, you should have a basic understanding, right? If you have basic understanding, you have good knowledge of the network, then you should be able to build this one, okay? This one, or at least understand it. We you instead of LC filter, I think we use a transformer to model this one. So transformer equations, again state space equation for the transformer we build. So complete model of inverter now. So this is inverter model. Okay. Combined model of all inverters. Now we have in our system, I think we have 3 inverters. We are modeling 3 inverter together. So this is just inverter state space model. Okay. Then line state space models of the lines, simple, very first order equations. And this is the state space model of the line, right? Combine, okay. And then load model, load state space model. This is a load state space model. And if we put complete all together, then we have model of the complete microgrid. 3-phase model, state space model, small signal stability. And each, I think, inverter has 13 states. Okay, so if you have n inverter, that is n times 13. Okay, I think we had about 69 or 72 states in our system that when we were modeling. First thing that you do once you have state space, you analyze the eigenvalues. Simple, I think every master student, if you are PhD, then you definitely know how to do the eigenvalue analysis, right? And eigenvalue analysis tells whether your microgrid is stable or not. If it is not, then you need to modify or basically a matrix by adding some kind of K, right? So you can do. You can also analyze. We talked about system. Remember, microgrid stiff systems, right? So when you are doing simulation, we have not done that. But when you are doing simulation, and this, okay, let me talk about very important one. These are the 3 things that I think we learned. So from A matrix of a system, eigenvalues of system can be determined and plotted, right? Eigenvalues can be separated into high frequency, medium frequency, and low frequency eigenvalues. Sensitivity analysis shows that high frequency, sensitive to LCS filter, transformers, and line currents. Okay, these are medium frequency, sensitive to voltage and current controller, gains, and LC filter, and low frequency, right? So that is sensitive to power controller, gains, and that basically the eigenvalues that are very near to 0, right? Very near to 0. These are fast dynamics, right? Time constant here is large, time constant is smaller. So these are the high frequency. So these devices are affecting the poles of the system or response of the microgrid. Okay, that is slower response. This one is faster response. For faster response, that the power controllers gains, right, are affecting the microgrid's response. Okay, so very important. Balance system. So we did all 3 units. Inverters are producing same amount of power. Okay, so we did this control and reactive power mismatch. Very beautiful this graph. Okay, see what it is demonstrating here. So this is DG, the difference, DQ difference, right? Delta change, load change, right? So that's the difference between this here, and then before the disturbance and after the disturbance, right? So after load change, before load change. Now with the new controller, we are still within very similar to what we had before. Okay, what we had before compared to the available outside means this. And this is the new controller that we designed, Q controller. Okay, so I think that's our contribution on this one. Okay. So very important. Q control is also. Troop control, adding load, okay, islanded mode, different controller, and we can see that our controllers are working here, okay, and sharing the active and reactive power both. So this is reactive power sharing, these are active power sharing, okay, between inverter 1 and inverter 2 in this case, okay. Challenges with unbalanced system and assumptions of balanced microgrid system does not hold true for an actual microgrid system. A low voltage distribution system is generally unbalanced due to unbalanced lines, right? That we already discussed. Determining eigenvalues of such system for small signal is difficult as A matrix of such system cannot be determined easily, okay? Controllers used for balanced system may not be adequate for unbalanced system. That's what we learn, okay, very important. Okay. Unbalanced system. Here we have P1, P2, and P3, three inverters. When using controllers derived from balanced system, we can see that power oscillates between inverters in unbalanced system. Okay, so here, so balanced system applied on unbalanced system. Okay, and we see that power oscillations here. This means frequency also oscillating. P oscillate, P is directly proportional to F. So if P is oscillating, then frequency is also oscillating. So we did this one, okay. Solution for unbalanced system, unbalanced ABC signal, okay. That is voltage and current can be decomposed into their sequence components. This helps in obtaining D and Q quantities which are independent of each other. But this increases number of controllers. It means controller for positive, negative, and zero DQ. Okay, so that is the solution. You have to have all controller mean for all. With that, I think voltage and current controller with DQ frame basically. So each controller requires two subcontroller for controlling positive and negative sequence. System can be controlled. However, eigenvalue analysis is still a challenge. Okay, still a challenge with this one. So I think it's a good time. So I think I covered most of the things that I had planned, and the last thing that we do is open DSS. Okay, so I will log in from another system, and then I will probably share a link for you to download, and let's work on that IEEE 13 node system. Okay, on open DSS. Okay, so let me stop sharing screen here. Okay. Give me some time, okay? Maybe a couple of minutes. You can later download the latest version. Okay, so I'm just giving what I have so that it works with what I have. Okay. Okay, so I'm sending a link here. Give it like maybe a 30-second or a minute, and then you should be able to accelerate. Okay, let's do that one. Okay. Dr. Prerna, I may be joining from another computer. Okay. What thing we need? Okay, anyone is installing this software or not? These are the two things that we need. Okay, Sailendra. So two OpenDSS, one, and then, okay, thank you. Okay, so go to these two websites, okay. One is the data for and the base case from the IEEE committee, and one is the OpenDSS APRI software, older version, okay, but you can do it later on newer version as well. Okay. Okay. If you got both of them, please can you write here on the chat message that you got both file. You can open Word file from that feeder 13.zip, and you can open opendss.dll file from that zip from drive.google.com. If you can do both, then just write me here so that we can go to the next step. Remember, we don't have enough time, but I think I can still at least point you, show you what it is, what it entails, and then how you can perform distribution power flow. And then a lot of resources available once you know this one to do time domain. And if you want to do some kind of MATLAB COM interface, okay, so those are for PhD student for sure. If you are working on this one, this side, yeah, some kind of secondary control, okay, some kind of multi-level agent based control, microgrid, I think those are the good thing to do. Okay, I will give 2 minutes, okay. Okay, fill up my bottle. Let's talk a little bit more. Okay, so that's it. Very good, very good. Okay, so we have at least a couple of students. Very good. So let me now share my screen here on another computer. Okay. So this one is 13 node file, right? 13 node, very well designed, small system with expert knowledge. This is 13 node is why it is important. It is because it has 3-phase line, distribution line. It has distributed load. It has 3-phase transformer, single phase transformer. It has capacitor. It has all kinds of load. Okay, delta load, Y load. Let's see here. So configuration, overhead line configuration, different configuration. You have a BAC, CAB, CBN, ACN, right? So these are kind of academic case, okay? So you won't have this kind of configuration in real system, but it covers a lot of aspects of the distribution system, okay? Then 3-phase here, ABC, generally you will have ABC, you will not have BAC, okay? On this one. Spacing ID, right? How it is spacing. This is 500, 515. I was explaining you how spacing works. Line segments, these are line segments, length of the lines, and what is the configuration, right? So out of this 603, so you come back and say 603 CBN configuration, okay? And spacing is 505. With this information, we should be able to calculate the Z of this line, okay, basically. Similarly here, 671 to 684, line length is, 632 to 678, line length is 2000 feet. And the configuration is 601. You come back here, 601 is BAC, and spacing ID is 500, okay. Transformer, substation transformer, capacitor bank, you have 3-phase, single phase capacitor bank, right? So very detailed, very well thought, 13 node regulator, voltage regulator is there. Spot loads, you see, constant PQ, Y connected, constant Z, delta connected, PQ, delta connected, constant current, okay. So all kinds of loads, so constant current Y, right? And then if you see we have 3-phase load, you have single phase, B phase load, A phase. So all kinds of load. So, and then you also have a distributed load on this one. So very, very good 13 node. And that is why you will see anytime when you have some kind of research, you will see 13 node system. Okay, so now once you have this one, you can calculate this one based on your configuration spacing, you get these values, okay? And here we are just representing diagonal and upper triangular matrix basically, okay? B matrix 10 to the power minus 6, you can ignore it, or if you want to, you can model it if you want, okay? So different Y's for all the lines, okay? This is line model. All line. So let's start with now, if you have opened your OpenDSS, and I gave you 13 node file, it's called IEEE 13 node matched published WVO results, okay? This is, I work on this one. And then if you go to this one, I work with my wife here, Sarika Kusalani Solanki. So 13 node circuit name. So this is.
Good morning, sir.
Say it again.
Sir, in here, in data 13 was unbalanced data, there is a regulator data, sir.
Okay.
So in the regulator data, sir, when we design in MATLAB regulator, the internal resistance we need to find, sir.
Right, right.
Sir, actually, I have problem with the finding of internal resistance of that regulator, sir. Can you tell me?
See, so are you able to see why it's not showing this? Okay. Sorry, why I thought you are seeing my screen, but on my screen,
Yes, sir, I am seeing, but in that regulator data, we have to see how to find.
Yeah, that's what I'm saying, that we have something that I want to show you. I don't know why. Let me see.
Okay, sir.
1 second. I think, okay, I understood that one. Okay. Okay, so if you have not opened, just please open this file. Where is my file? 13 bus. Okay, so not this file. DSS. This one. So you need to open this open DSS.dll or exe, whatever the file is. Once you open it, you will have something like this, and then you open your 13 node match publish file. You come back here, 13 node. I think I did give you that file. Somewhere should be there. Okay, 13 node match file. I gave you that file, so you open it, you will have something like this. Okay, in your system, in your file. Anyone could do that? We have at least 1 or 2 students who can do that. Okay, very good, Subha. So now once you open it, you have, we start with this command, new. Generally, we generally don't write it. We use any publish file and then modified. Okay. So new circuit dot this one. So that's our circuit name is 13 node circuit. Okay. It has a base KVA 115, per unit value 1, phase is 3, source 1, right? Bus 1 has a source bus. Angle, whatever the angle you want to give, right? Advanced angle 30 degrees, so results agree with published angles. Okay, so starting with this is again unusual, right? Means so this is academic case. We start generally with 0 angle. Okay, short circuit capacity, these are all model. So now we are coming back to, so someone was asking for regulator. Okay, so here regulator, I don't know what you mean by that one, but here we have a regulator, transformer, winding 2, voltage regulator, bandwidth, I think probably 2 volt here, turns ratios, and R and X 3 and 9. Okay, so 3 and 9 you used it from your data file. So R and X, that's is model here, R and X here. Okay, this one I don't know what that's what you were mentioning, or you were saying that how to calculate it.
Sir, actually, this is the R and X setting.
Right.
I think so. It is internal resistance is something different from this, I think.
But this is what we model. Okay, so R and X setting, internal resistance. So if you want to go and investigate this, and if you are talking about the steady state modeling, so look at the model given in Costing book. So he has even given solved problem with the regulator. So that's it. Okay, so look at it and probably it will help you on that direction. Okay.
Which book, sir?
Costing. I don't know, power distribution. Costing. Just type costing on the Google. Let's see. Costing. Power distribution system modeling, I think. Distribution system. Professor Costing, William Costing. William.
Nice.
Okay, this is the book. Okay.
Sir, I gone through this book, sir, actually. But
oh,
I didn't...
so it's not providing that information?
That information is not here, sir.
Oh, okay. So then I don't know. I don't know. I have to look at it, Sarasi. So it's not in top of my head. Okay.
Okay, sir. Okay.
Okay. Yeah. Okay. So then you model your regulator. Okay. So this is a regulator modeling. We have 2 regulator, regulator 1, regulator 2 in 13. Oh, we have 3 regulators. Okay. So we are modeling that one. Transformer, we are modeling what are the buses, Y connections, right? What are the voltages, KVA rating, and R, and high side and low side of this one. Main one is this one. This is what we were actually interested in, line code 601. So that's line code 601. So come back here to this one. So we are modeling this 601.3465 and 1.0179. So you come back here to your distribution file, 0.34, and then you are modeling R and X separately. R and X, and then B matrix, generally we say C matrix here in OpenDSS. So R, X, and B we are modeling here. So these are just upper triangular matrix 0.34 here and 1.0179 here. Okay, so that's your R and X, other values of R and X here. So let's go back here again to this one. If I can do side by side, that would be great. Okay, so that is 0.1560.3375. So 0.1560.3375, right? So then we are modeling all this basically X. So 601 lines, 602 lines, all the lines we are modeling here. Simple. Load models, we are doing load models. Okay, so let's go back to the load model. Let's see if we can shrink this one. Okay. Shrink. Then put it on side by side, that would be good. Okay, so load model this one, and then we can put this also side by side. Okay, this would be better. Okay, and then so we can model all the Z's. Okay, all the calculation details are given in that book that I just mentioned. Okay, spot loads 671, load 671 here. Okay, is delta connected PQ, and all these values are given. Okay, so it's ABC 1 2 3 is for ABC here. Okay, there are 3 phases. Connection is delta. Model 1 stands for PQ, so it's constant PQ load. Whatever the voltage of that nominal voltage, and kilowatt and kVAR here, right? 115 is probably, this is 3-phase balance load problem, probably. Okay, divided by this one. Or no, I think 671, yes. Looks like it's a balance load, okay? And then 634, on this one, 634, Y connection PQ. So 634, we have 1 2 3 different load in each phase. So 1 2 3. Okay, so yeah, so 671 is balance load. Okay, so we combine all together. So we are putting here 3 phases. Okay, because we are modeling, so the software knows that we are giving 3-phase balance load here. So phase A, phase B, and phase C. Okay, and here when we say Y, it automatically knows that we are talking about line to ground voltages here, right? So these are line to ground voltages. Each phase 160, 110. So we are modeling 160, 110. Model is here still PQ. Okay, PQ model 1. So ABC phase. So A, B, and C here. And then we have 645. 645. Now you see we have load only on phase 2, right? Phase 2 we have. And this is Y connected, again PQ. So 645 2 and 645 3, right? So this one is model 1 kV, this one 170 and 125. Okay, there may be another, so that is 646. Okay, let's do constant Z1. Okay, so this is 652, load at 652. If you are following, Y connected, constant Z, and only in phase A. Okay, so that is 652. Let's search for 652. So only one phase load here, 652 we have. Phase is equal to 1, connection Y, model 2, 652 is constant Z, model 2, okay, constant Z, probably model 2 is constant Z, but you can refer to OpenDSS user manual. Okay, so you should be able to find this information. Probably I might have opened somewhere. Nope, not here. Okay, so this is basically your modeling, load model in your distribution system. Okay, and then We have capacitors. Okay, capacitor 1, capacitor 2, models here. There are my capacitors, regulators, model capacitors. Okay, so 200, 200, this one. So we have balance, and second one is so 611 only on phase 3, and 675 is all phases, phase equal to 3. So 3 phases capacitor. Okay, and then we have these are the lines. Okay, these are the line codes 601. So and then we are saying what is phase 3 line, regulator 1, 2, 3, right? So these are the lines we are modeling here. These lines we are modeling 632, 635. Right, the name say 632. So whatever the name you can say, but the line phase 2, right? And then line code 603, length of the line 500, and feet. So this is what we are modeling. Then whenever the transformer 633, 634, where is we have 633, 634. Don't see it. I don't see 634. That's the transformer. Okay, so that's a, and then we have I see somewhere regulator. Okay, 650, 632. 650, 632, that is the, I don't see regulator here. So that is 3-phase regulator here, 650 and 632, right? And then line code for this one. Okay, then you can model that one. Okay, so all the lines basically are modeling here. Switches. Okay, switches are also modeled as line, but if switch you say yes, and then you model at very small impedance of the switch, very small impedance of the switch. Okay, set the voltages, calculate Y, that's the command, and solve. When you say solve, it will solve the power flow, and it is uses some kind of bus coordinates from here. Okay, so I think probably most likely we are ready to do the distribution system power flow basic. Okay, and these are some of the results that we have here. Okay, let's say we select, control all, and then we do right click and just say do select. Okay, and then it will probably not found. Okay, open DSS 337. Okay, let me open file that way. How? Let's see. You can run it, that would be great. Let's see. Same file, control on. Okay, so we got something. That's good, right? You can see this one. So do select and you run the power flow. Okay? Now we can verify our voltages. Let's to start with regulators. Okay, regulator voltage here. These are the power flow results. Where are the voltage results here? So these are the results here. Okay, so these are the reported by the committee. Okay, and tested, approved. See what we got, 1.622 here. So we got here 1.0625. Second phase 1.0498. Here 1.05. Very good results we can consider. And then 1.0684. 1.0687. Okay, so very closely matching with the published result. Okay, so once you have this kind of, so anytime when you are doing this your work, you should have some kind of benchmark. Okay, so if you are doing for any research, benchmark is very important. Like I was mentioning, for microgrid, benchmark is Badriram paper that we use. That's the researcher that we used. So benchmark, so whenever we are doing, so we have many other publications that we have not talked about it. So we use the previous published reproducible papers, okay, and then we implement our new algorithms on it. So I think it's a good time to stop, and let me ask you a couple of questions. Okay, so give me like 1 or 2 minutes. Okay, let me stop sharing here. Give like 2 minutes, okay? Okay then. Okay, I prepared 3 questions, okay? And let's see. And congratulations to all the students who spent 20 hours or 25 hours with me, okay? So that's quite an achievement if you are really listening and understanding and trying to understand. So that's kudos to you all, okay? So please, can you just quickly, I have 3 questions to ask. And then you will be headed for your dinner. Okay, quickly, guys. We have 39 participants, okay? So at least 30 students will quickly die so that we can go to questions. 1 question, actually, 2 questions, 3 questions, simple questions. Okay? Okay, we are running out of time. Okay, let's go. Okay, that's quite an achievement, right? Not single student said no. Okay, so that's a good thing. Okay, that's a good thing. I don't know whether it will allow or not, but looks like it should allow the email address. Next question is very personal to me because I am coming to India and I want to hear from you. Means what are the vacation spots that you would recommend? I'm coming, me, my wife, I have a 13-year daughter and 8-year-old son. Okay, so when we are looking to spend maybe a week somewhere in a nice vacation spot, India. So what you will recommend? So I would really appreciate, that's a personal question. So maybe if you can write multiple, that's fine. Okay, so just write and then I will go through it during my travel. Okay. Any something unique that would be great. Yeah. Tree houses or something unique, something, yeah. Whatever comes to your mind. Okay. I should have given a little bit more time on that one. Okay. Okay, awesome. At least no one wrote Mumbai, so that's a good thing. Okay. Okay, so I think that concludes our session here, 5 days. So we should thank our Gyan Ministry. We should thank MNIT leadership team. We should thank Dr. Prerna, Dr. Rohit, and all of you that you survived today. 5 days gruesome 4 hours learning. Okay, and I think I congratulate all the students who really were keen to learn. Okay, so and that's all I have to say. I mean, anything, Dr. Rohit or Dr. Prerna, I don't know. Okay.
Thank you so much, Dr. Jignesh, for your patient teaching, that I would say, for 4 long hours every day, patiently and in the same mode, in the same man. Your energy level, which is at the start of the lecture class, remains till end. From our side, 5 p.m. to 9 p.m. Same energy level is there. So that is really commendable
Thank you, Dr.
something
Prerna.
to learn from our side. And here at this valedictory end of this Gyan course, we have organized a small valedictory. I am there, Dr. Bhakar is there. And I would invite any of the participants here, if they are interested, they want to say something about this course, a small feedback. We would appreciate if they can give us, they can put on their camera and give us a feedback for the course. Like Manveer is there with her camera on. So I invite her to say, your mic is off. Your mic is off. So hats off to Dr. Jignesh sir from Shalinder Gupta, to everyone. Priya Kumari, to everyone. Thank you, sir.
Thanks, Dr. Prerna Jain, for organizing such a good course. And this is the first time I have learned something about the multi-agents. I've never heard of about this earlier. So I will try to collect my knowledge in this field as well now, from now onwards. And I feel this is a very good course. We have a course in program in electrical and computer engineering at our institute that we have started 2 years back. And the student will be in 3rd year. And we are looking for what could be the courses which should be taught to the students of electrical and computer engineering programs other than our core electrical and core computer courses. So this is one course which is coming to my mind, that we should teach them multi-agents so far as we can say the automation of the grid is concerned. Okay, so that's a very good idea which has given to us. Thanks, Dr. Jignesh, for sparing such a wonderful time to us and giving us, imparting us the knowledge about this new field. Thank you so much, ma'am. Thank you so much, sir. Thank you.
Thank you.
Thank you, Manveer. Thank you. So it is actually, it has been it has come to my surprise, Dr. Jignesh, that most of the participants here are from best institutes of the country. Like you could see today at the start of the lecture as well that the participants are from, and they are the faculty in the institutes, and they have the urge of learning new things, which is commendable. And
that's absolutely right, Dr. Vanna. Very good notice, means I think that's absolute. And they were keen, right? I mean, some students are they really want to see, means learn. So
like Manveer's faculty, then we have some faculty, I think, from NIT Karnataka, then from NIT Hamirpur. And I cannot remember because actually 80 participants registered. Actually 40 have been active, but that is also a good number.
That's true. That's true. Yeah.
After the inauguration, Dr. Vijay Jinyani called me and said, how come you got 80 participants? I think I said maybe because of the content of our course.
Okay. Very good.
Because most of the pictures we have on the Gyan page of our institute, there are only 20-30 participants. So that is why he called me.
Got it. Oh, you must have done some good work, Dr. Prerna. So you should congratulate yourself on that one.
I'm thankful to my PhD students. They actually distributed and really worked on the publicizing this course. And of course, the content. Okay. Both the things went together. So that is
Dr. Rohit, when did we meet in NEFS? Where I think PS General, I remember.
I think we have been meeting in the PS General meeting.
Right. Yeah.
Quite regularly. And that was how, when I came to know that you are interested, we caught you up for the program.
Okay. Yeah.
In fact,
I just wanted, sorry.
In fact, I'll be visiting PSGM this year as well.
Okay.
Yeah. So, in fact, I had been following up what you have been doing, and in this course also, it was quite interesting. Because not only, one good thing was that people, not only from electrical engineering, but from other domains are equally interested in learning this domain. Yeah. So a couple of my colleagues from mechanical and other departments, they were also equally interested that, okay, this is a domain that we should learn.
Yeah, I mean, that's very, very important. I mean, nowadays, decentralized control is very important. And for microgrid, especially for development, R&D, that is the tool, I would say, for that, yeah.
I think at the end, I would like to thank the ministry for providing this platform where we can learn from faculty members who are working in top universities across the world. And also thanks to the participants, faculty members, students who are participating and learning the skills basically, which can help them to bring at par with the international research that is going on. Most of it, the content, since it is coming from what has been taught at your university, obviously it brings value to us, all those participants who are attending it. So thanks to you for sparing time. It is, as Dr. Prerna indicated, it is a long lecture taking so many hours every day. Yeah. It is quite tiring, I understand.
I know I had no life for last 5 days. Probably I will breathe today. So I was just eating and that's it. So thanks to my wife, actually, I would say that because we have to pack, right? We have like so many suitcases, so many things. She is somehow holding it. So I'm really thankful to my wife that she just let me do this 5 days uninterrupted. Means. So I think that I'm very, very blessed, I would say. Very important, right?
Yeah, this is actually for you. It is very tough time.
And I'm traveling tomorrow.
Shailendra Gupta is saying, and my wife as well, who let me do it.
Okay. Good. Okay.
So, Dr. Jignesh, once you are in India, possibly we'll plan for half an hour lecture whenever you are comfortable for our faculty members and students. So
sure. Means means you tell me
whenever it is comfortable to you.
I mean, after 1 week, I think.
Yeah, that would be fine.
Because I will remove my jet lag.
Yeah.
Can just, it could be not a lecture, but we can just like you said, ask questions.
Yeah.
Or talk about it. Maybe I can.
What all research is happening out there in your university, in your group, that should be sufficient for us.
Okay. I think that's
yeah.
Okay.
So for how long you are visiting India?
Long time, I would say. Long time. We are blessed, I would say. We got a little bit long time, so we'll be spending more time.
That is why you're planning to visit different places.
Different places, yes.
Yeah.
My wife lives in Nagpur. I live in Ahmedabad, and I have roots in Ahmedabad. So that are the 2 places. And then my wife was saying that let's go to Jaipur. I said it will be very, very hot.
It is quite hot. 47, 46, 47 is the temperature in the afternoon. But we are expecting to get rains by 15th June. Then I think the things will be fine.
Okay then. And Dr. Rohit, Dr. Prerna, I talked to my department chair, is Anurag Srivastava, and he said that he is working with Dr. Padhi, Padhy, Padhi, right?
Yeah, who is our director.
Yeah, okay. So then I said that, okay, then I will be out. Means you can do. So they say that he will contact Dr. Padhi, and if your institution is interested for some kind of MOU, and he will work out something. So I just remove my hand on that, but let me know if you have any help in it. But I conveyed my information, because like I said, that is not beyond my place.
But definitely, thanks a lot for putting in the words. I'll talk to Professor Padhi, and possibly he'll get in touch with Professor Srivastava out there. Yeah, that would be good.
Okay then. Hey, thank you all the students, and good luck. Whatever you do, do it with the passion, and make that whatever you are doing is the primary goal for you, and then no one can stop you. If you do it that way, no one can stop you. Whether you are coming from whatever university, whatever background, no one can stop you. That when you make your aim, your primary goal is to whatever you want to do. Very important. Thank you very much.
Thank you. Thank you, Dr. Jignesh, and thank you all the participants. Thank you. And we suppose then you get registered in other forthcoming courses as well. As the enthusiasm is shown for this course, we expect for other courses as well.
Okay, sure. I would love that. Yeah. My wife, in fact, was saying that let's go and deliver this to some Australia or somewhere. Let's see how it goes. Thank you very much. Okay. Good night, everyone. So I'm logging out.
Thank you.